Look up at the night sky, at that breathtaking tapestry of stars and galaxies, and allow yourself a moment of awe. It feels complete, doesn't it? A brilliant, glittering universe laid out before you. But what if I told you that this magnificent spectacle, everything your eyes can perceive and every telescope has ever captured, is nothing more than a ghostly afterimage? A cosmic illusion, the stunning truth, one of the most profound discoveries in all of modern science, is that this luminous realm of planets, suns, and nebulae, the entire universe of light and time, as we know it, makes up less than 5% of everything that actually exists. The rest, the overwhelming majority of our reality, is composed of something entirely different, something we cannot see, touch, or directly measure. We are about to embark on a journey to unveil the universe's dark side, a hidden domain ruled by two of the greatest enigmas in physics, dark matter and dark energy. This isn't just a story about distant galaxies, it's a revelation about the very fabric of existence, a journey beyond the limits of light and time into the profound darkness that truly governs the cosmos. For centuries, we have built our understanding of the universe on what we could observe, trusting in the light that traveled across the void to tell us its story. But that story was radically incomplete. The discovery of the dark universe is a humbling reminder of our own perceptual limits. We are like deep-sea creatures who have only just begun to understand the concept of water, unaware of the immense pressures and vast landscapes that exist just beyond our senses. The cosmos we thought we knew is merely the visible tip of a colossal, invisible iceberg. This journey will take us from the first whispers of this hidden reality in the work of pioneering astronomers to the cutting-edge experiments that are now hunting for the elusive particles of dark matter in abandoned mines and trying to measure the repulsive force of dark energy as it pushes the very fabric of space apart. We will explore how dark matter acts as an invisible skeleton, holding galaxies together and weaving the immense cosmic web, and how dark energy is orchestrating the universe's ultimate fate, driving an expansion that is not just continuing but accelerating into an ever deeper darkness. Prepare to have your perception of reality fundamentally challenged. This exploration is not just about filling in the blanks on a cosmic map, it is about redefining the map itself. The familiar rules of physics, the comforting certainty of a universe governed by what we can see, all of it is up for grabs. We are peering into the shadows, and what we find there promises to be stranger and more magnificent than anything we have ever imagined. So join me as we set aside our assumptions and step into the unknown, ready to confront the deepest mysteries of the cosmos and uncover the truth about the dark side of the universe. Our story begins not with a flash of light, but with a puzzle buried in the quiet calculations of a brilliant and often cantankerous astronomer. In the 1930s, a Swiss scientist named Fritz Zwicky was studying the Coma cluster, a vast collection of over 1,000 galaxies bound together by gravity, millions of light years away. Zwicky was a formidable character, known for his sharp mind and equally sharp tongue, and he applied a powerful new method to understand the cluster's mass. He measured how fast individual galaxies were whizzing around within the cluster's gravitational grip. What he found was deeply perplexing. The galaxies were moving at such tremendous speeds that the collective gravity from all the visible matter, all the stars, gas, and dust they could see, was utterly insufficient to hold the cluster together. According to all known physics, the Coma cluster should have flown apart eons ago. It was a glaring contradiction. To explain this, Zwicky proposed a radical idea. There must be some other form of matter present, matter that did not emit or absorb light, providing the extra gravitational glue. He called it dunkel materie, dark matter. It was a whisper from the void, a ghostly suggestion that most of the universe's substance was missing from our picture. Yet for decades, this revolutionary idea was largely dismissed or ignored by the astronomical community. It was too strange, too far outside the established paradigm, a solution in search of a problem that many felt must have a more conventional explanation. The puzzle lay dormant for nearly 40 years until a meticulous astronomer named Vera Rubin picked up the thread. In the 1970s, Rubin and her colleague Kent Ford were not looking at entire galaxy clusters, but at the motions of stars within individual spiral galaxies. They focused on measuring galactic rotation curves, which are graphs that plot the orbital speeds of stars against their distance from the galactic center. The expectation, based on Kepler's laws of motion, the same laws that govern our solar system, was clear and simple. Stars close to the center, where most of the visible mass is concentrated, should orbit very quickly. But stars out in the sparse, dim outskirts of the galaxy should be moving much more slowly, just as Pluto orbits the Sun far more sluggishly than Earth. What Rubin and Ford found, to their astonishment, was that the rotation curves were flat. Stars at the very edges of these galaxies were whipping around just as fast as those near the center. It was as if every planet in our solar system, from Mercury to Neptune, orbited the Sun at the exact same breakneck speed. This was impossible if the galaxy's gravity came only from the glowing stars and gas they could photograph. The only plausible explanation was that each galaxy was embedded within a gigantic, massive halo of something invisible. This unseen substance had to be far more abundant than all the luminous matter put together. Its gravitational pull, the only thing preventing those high-speed outer stars from being flung off into intergalactic space. Vera Rubin's work provided the undeniable, observational proof that transformed dark matter from a fringe curiosity into a central problem of modern astrophysics. Her data was so clear, so consistent across dozens of galaxies, that it could no longer be ignored. Here was the foundational mystery laid bare. The universe was not made of what we could see. The stars and nebulae were merely the decorative lights strung upon an invisible framework, a framework built from a substance that neither reflected nor emitted a single photon of light. The work of Zwicky and Rubin, separated by decades, established the first major player in our cosmic drama. They revealed that the cosmos we perceive is just the surface of a far deeper and more mysterious reality. A reality where the dominant form of matter is completely hidden from our view, detectable only by the ghostly tug it exerts on the things we can see. This was the dawn of our understanding of the cosmic darkness, the moment we began to realize that we are living in a universe of shadows where the true actors remain backstage, their presence felt but never seen. So we know dark matter is out there, its gravitational signature undeniable. But what is it? This is where the mystery deepens from a simple observation into a profound puzzle of physics. Dark matter is not just empty space or a void. It is a specific type of substance, a form of matter that fundamentally ignores light. It does not emit it, it does not absorb it, and it does not reflect or scatter it. To every telescope ever built, from the humble optical scope in a backyard to the mighty James Webb Space Telescope peering into the infrared, dark matter is completely and utterly invisible. It is a cosmic ghost, and we only know it exists because we can see the footprints it leaves in the gravitational fabric of space-time. Its presence is a conclusion we are forced to draw from the way it tugs on the things we can see. The way it whips stars around galaxies, bends the light from distant quasars, and dictates the grand architecture of the cosmic web. To grasp its nature, it helps to contrast it with the normal matter we're made of, the stuff scientists call baryonic matter. You, me, this planet, every star in the sky. We are all composed of protons, neutrons, and electrons, particles that interact with each other through multiple forces. They crash into each other, they repel each other electromagnetically, and they can be heated up to glow with brilliant light. Dark matter is thought to be entirely different. It doesn't seem to participate in this vibrant electromagnetic dance. It doesn't form atoms, it doesn't create molecules, and it can't collapse to form stars and planets. It simply passes through the ordinary world, mostly unaffected. Think of it this way: if the visible universe were a grand, intricate city of light, dark matter would be the underlying bedrock and landscape upon which that city was built. The city is what we see and experience, but the bedrock is what gives the city its shape and stability, even though we rarely think about it. A key property that helps explain its role is that it's considered cold. This doesn't mean it's icy, but rather that its theoretical particles move relatively slowly, especially in the early universe. This slowness is crucial. In the hot, dense conditions just after the Big Bang, normal matter was coupled with intense radiation, a searing plasma that prevented it from clumping together easily. But cold, dark matter, unaffected by this light, was free to start gathering under its own gravity right away. It could form small clumps that then merged into larger ones, creating gravitational wells, cosmic potholes into which normal gas could later fall. This cold nature allowed it to act as the universe's foundational scaffolding, providing the initial blueprint for all the structure that would follow. If dark matter were hot and fast-moving, it would have streamed smoothly across the cosmos, smearing out these initial seeds and preventing galaxies from forming in the way we observe. Its slowness was its power, so what could this invisible substance possibly be made of? The leading ideas are as fascinating as they are elusive. For decades, the prime candidate has been the WIMP, or weakly interacting massive particle. As the name implies, these are hypothetical particles that have mass, hence they feel and exert gravity, but interact with normal matter only through the weak nuclear force and gravity, making collisions incredibly rare. There's an elegant, almost magical reason physicists like this idea. Calculations show that if such particles did exist in the early universe, they would have been produced in just the right abundance to naturally account for the 27% of the universe we now attribute to dark matter. This coincidence, known as the WIMP miracle, has driven a multi-decade global hunt to detect one. A compelling alternative is the action, a particle originally proposed to solve a completely different problem in particle physics. Actions would be billions or even trillions of times lighter than an electron, ghostly wisps of matter that could collectively make up the dark universe. In some theories, they are predicted to convert into photons in the presence of a strong magnetic field, a faint signal that dedicated experiments are now trying to pick up, like listening for a whisper in a hurricane. Other possibilities abound, from sterile neutrinos to theoretical particles emerging from extra dimensions of space. The very diversity of candidates shows how wide open this field remains. We are surrounded by this substance. It makes up over a quarter of everything, and yet we still do not know its fundamental identity. It is the ultimate game of cosmic hide and seek, and we are just beginning to understand the rules. Now let's pull back from individual galaxies and look at the universe on its very largest scale. If you could take a God's eye view of the cosmos, seeing billions of light years in a single glance, you wouldn't see a random scattering of galaxies. Instead, you would witness one of the most majestic and humbling structures in all of existence, the cosmic web. Picture an impossibly vast, three-dimensional spiderweb, stretching across the entire observable universe. Glowing knots where thousands of galaxies swarm together in massive clusters are connected by long, shimmering filaments of star systems, and between them lie immense, dark, and nearly empty voids, regions of staggering emptiness that can span hundreds of millions of light years. This is the large-scale structure of our universe, and it is not an accident. This magnificent architecture, this cosmic metropolis, was not built by the stars and gas we can see. They are merely the inhabitants, the lights in the windows. The entire structure, the skeleton itself, is built from dark matter. Think of dark matter as the unseen framework, the steel girders and concrete foundations of a colossal skyscraper, while the visible galaxies are the illuminated rooms and decorative facades. We see the beautiful lights, but it is the hidden skeleton that gives the entire building its shape, strength, and stability. This is not just a poetic analogy. It is a conclusion driven by some of the most powerful supercomputer simulations ever run. Projects with names like the Millennium Run and Illustris TNG start with the initial conditions of the early universe, a nearly smooth soup of matter and energy, and then let the laws of physics play out over billions of virtual years. When they program these simulations with a universe dominated by cold dark matter, something remarkable happens. The dark matter, responding only to gravity, begins to clump. It collapses first into an intricate web-like network of filaments and halos. Then, and only then, does the normal baryonic matter, the gas, feel the pull of this pre-existing gravitational landscape and begin to flow. It streams along the dark matter filaments, cascading into the gravitational wells at the intersections, where it condenses, heats up, and eventually ignites to form the galaxies and clusters we observe. The simulation and the real universe match with breathtaking accuracy. Without this dark matter scaffolding, the universe would be a profoundly different and likely much lonelier place. The force of gravity from visible matter alone is far too weak to have pulled together such an elaborate cosmic city in the 13.8 billion years since the Big Bang. The gas would have remained too diffuse, the initial ripples too faint to grow into the grand structures we see. There would be no great walls of galaxies, no dense clusters, and possibly no large galaxies at all. The cosmos would be a sparse, dark sea with only isolated islands of stars. So, from the very origins of the cosmos, dark matter has been the primary architect. It dictated where the first galaxies would be born, it guided their mergers and growth, and it continues to hold the entire visible universe in its gravitational embrace. Every glittering city of stars, from our own Milky Way to the most distant quasar, exists because it formed within the invisible, unwavering grasp of a dark matter halo. This hidden blueprint is the true map of the universe, a map we are only just learning to read, and its discovery points toward forces even more mysterious and powerful at work in the cosmic shadows. Just as we were coming to terms with the idea that most of the universe's matter is invisible, a second, even more profound shock was waiting in the data. For decades, the central question in cosmology had been a simple one: how fast is the expansion of the universe slowing down? Everyone, from the most esteemed theorists to budding students, was certain of the answer. The mutual gravitational attraction of all the matter in the cosmos, the combined pull of every galaxy, every star, and every speck of dark matter was acting like a cosmic brake, gradually slowing the expansion that began with the Big Bang. The only real debate was whether there was enough matter to eventually halt the expansion and cause a big crunch, or if the universe would simply coast forever, expanding more and more slowly into an endless, fading future. The idea that the expansion could be speeding up was not just unexpected, It was, for most physicists, unthinkable. This paradigm-shattering discovery was made not by a single individual, but by two fiercely competitive teams of astronomers in the late 1990s, both using the same cosmic mile markers, type Ia supernova. These stellar explosions are some of the most dramatic events in the universe, but for cosmologists, they are precious tools. A type Ia supernova occurs in a binary star system where a dense white dwarf siphons material from its companion until it reaches a critical mass and detonates in a thermonuclear blast. Because this critical mass is always the same, the intrinsic brightness of these supernovae is remarkably consistent. They act as standard candles. If you know how bright something truly is, you can calculate its distance from how dim it appears from Earth. Furthermore, by analyzing the light's redshift, how much the expanding universe has stretched its wavelengths, astronomers can determine how much the universe has expanded since the supernova's light began its journey. The two teams, the Supernova Cosmology project led by Saul Perlmutter and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, were racing to measure these distances and redshifts for supernova billions of light years away. They were pushing to the edge of the observable universe, looking back in time to see how the expansion rate had changed over cosmic history. Their goal was to measure the deceleration. What they found, to their own astonishment and initial disbelief, was the exact opposite. The most distant supernovae were fainter than they should have been if the universe had been expanding at its current rate all along. The only way to explain this was if the expansion was slower in the past. The universe's expansion wasn't slowing down, it was accelerating. It was as if you threw a ball into the air, and instead of slowing down and falling back, it shot away from you faster and faster, defying gravity itself. This was a result so shocking that the teams spent months triple-checking their data, searching for any possible error. Had they miscalculated the dust obscuring the distant supernova? Was there some unknown property of the supernova themselves that made them appear fainter? But the evidence was robust and soon overwhelming. In 1998, they announced their findings to the world, and cosmology was turned on its head. The universe was being pushed apart by a mysterious, repulsive force. This force was dubbed dark energy, a name that captures its profound mystery. It was not merely an absence of something, but an active, dominant presence. Calculations soon revealed its staggering dominance. Dark energy makes up about 68% of the entire mass energy budget of the universe. Dark matter, for all its mystery, accounts for 27%, and all the normal matter, every star, planet, and human, comprises a mere 5%. The cosmos, it turned out, was primarily composed of this repulsive energy. The implications for the cosmic future are dramatic and, in a way, bleak. If dark energy continues to dominate and behaves as we currently observe, the fate of the universe is not a fiery crunch or a gentle coast, but a cold, dark, and lonely disintegration. In this scenario, known as the Big Freeze or heat death, the acceleration will continue unchecked. Distant galaxies will first be pushed beyond our observable horizon, their light no longer able to reach us as the space between us expands faster than light can travel. The universe will appear to shrink around our local group of galaxies. Over trillions of years, star formation will cease, stars will burn out, and galaxies will fade to black. Eventually, the very fabric of space itself may be torn apart in a big rip. This dark energy-driven acceleration doesn't just change our model of the universe, it rewrites its final chapter, pointing toward an end defined by isolation and emptiness rather than a grand collapse. It is one of the most dramatic twists in the history of science, a story of a genius's supposed mistake that turned out to be a stunning premonition. When Albert Einstein was developing his theory of general relativity in the early 20th century, the prevailing belief among astronomers, including Einstein himself, was that the universe was static, eternal, and unchanging in its large-scale structure. His equations, however, told a different and deeply troubling story. They described a dynamic cosmos that should either be contracting under its own gravity or flying apart. To force his brilliant mathematics to align with the static universe everyone believed in, Einstein introduced a fudge factor, an extra term he called the cosmological constant, represented by the Greek letter lambda. This constant was a repulsive force, a kind of anti-gravity that worked against the attractive pull of matter on the very largest scales, perfectly balancing the universe to keep it still and stable. He later would call this his greatest blunder. That moment of revision came just over a decade later, when the astronomer Edwin Hubble, using the most powerful telescope of his day at Mount Wilson Observatory, made an earth-shattering discovery. By observing the redshift of light from distant galaxies, Hubble found that they were all rushing away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static at all, it was expanding. Einstein, upon learning of this definitive evidence, immediately saw that his cosmological constant was unnecessary. He had missed a golden opportunity to predict one of the most fundamental properties of the cosmos. He reportedly dismissed lambda as the biggest mistake of his career, and for the better part of a century, that's how the story was told, a cautionary tale about even geniuses meddling with their own beautiful equations. But the universe, it seems, has a profound sense of irony. The story of lambda did not end in 1929. It lay dormant, a ghost in the machinery of cosmology, until the late 1990s, when those two teams of astronomers made their shocking discovery of the accelerating expansion. Suddenly, the need for a cosmic repulsive force was back, and it was stronger than anyone had ever imagined. Einstein's discarded fudge factor was resurrected from the ash heap of history and placed front and center as the simplest and most elegant explanation for dark energy. The cosmological constant was no longer a mistake, it was a prophecy. It represented a constant energy density inherent to the very fabric of empty space itself. This concept is incredibly difficult to grasp because we intuitively think of empty space as nothing, a true void. But quantum physics tells us that the vacuum is not empty at all. It is a seething, bubbling foam of virtual particles popping in and out of existence, a dynamic medium teeming with latent energy. The cosmological constant is the embodiment of that energy. This energy of the vacuum has a truly bizarre property. It exerts a negative pressure. We are used to positive pressure, like the air in a tire, which pushes outward and wants to expand. Negative pressure does the opposite. It creates a sort of tension, a pull. And in the strange geometry of general relativity, this negative gravitational pressure doesn't just resist collapse, it actively causes the expansion of space to accelerate. It's as if every cubic centimeter of nothingness in the universe contains a tiny, relentless engine that is steadily pushing galaxies apart. This effect is so vanishingly small that within our solar system, our galaxy, or even our local cluster of galaxies, it is completely undetectable. The powerful grip of gravity from nearby stars and dark matter completely overwhelms it. But across the unimaginable voids between galaxy clusters, where matter is extraordinarily dilute, the accumulated effect of this energy in every cubic light-year of space becomes the dominant force, steering the destiny of the entire cosmos. This very subtlety points to one of the most glaring and embarrassing problems in all of modern physics. When physicists attempt to calculate how much energy the quantum vacuum should contain, the answer they get is wrong. Not just a little bit wrong, but catastrophically, monumentally incorrect. The theoretical prediction is a number that is 10 to the power of 120 times larger than the observed value of the cosmological constant. That's a 1 followed by 120 zeros. It is the single worst mismatch between theory and observation in the entire history of science. This chasm, known as the cosmological constant problem, means we are fundamentally missing something profound. Either our understanding of the quantum vacuum is deeply flawed, or our theory of gravity on cosmic scales is incomplete, or both. The resurrection of Einstein's cosmological constant did not solve a mystery. It unveiled a deeper, more fundamental one, showing that our quest to understand the dark side of the universe is far from over. So how do you search for something that is, by its very definition, invisible? If you can't see it, can't touch it, and it passes right through any material you try to put in its way, how do you even begin to map its presence? This is the monumental challenge facing scientists, and their solutions are as brilliant as they are diverse. They have become cosmic detectives, looking for the clues this invisible suspect leaves behind, and they've developed 3 primary lines of investigation, each operating on a completely different scale. We have the astronomers who study the universe's largest structures, the particle physicists who build exquisitely sensitive detectors to listen for a single, quiet click, and the cosmologists who read the fossilized light from the dawn of time. Together, they form a multi-pronged assault on the dark universe. The first technique is perhaps the most visually stunning, a direct application of Einstein's theory of general relativity that allows us to literally see the invisible by watching how it bends light. This phenomenon is called gravitational lensing. Imagine spacetime as a vast, taut rubber sheet. When you place a heavy object on it, like a bowling ball, it creates a deep depression. Now, if you roll a marble past that bowling ball, its path will curve, following the dip in the sheet. In the cosmos, dark matter, with its immense mass, creates these same kinds of depressions in the fabric of spacetime. When light from a galaxy billions of light-years away travels toward us and passes through a region dense with dark matter, its path is bent and distorted, just like that marble. From our perspective, the image of that background galaxy can be stretched into long, faint arcs, or smeared into multiple, mirrored images, creating what astronomers call cosmic mirages. By meticulously studying these distortions, by measuring how much the galaxy's shape has been warped, researchers can work backwards. They can calculate exactly how much mass must be present in the foreground to cause that specific bending of light. Time and again, the result is the same. The mass required is far, far greater than the total mass of all the visible stars and gas in that region. The only explanation is a massive halo of dark matter, its gravity acting as a colossal, invisible lens. This technique allows us to create detailed mass maps of the cosmos, effectively painting a picture of the dark matter scaffolding by observing how it twists the light of the universe behind it. The second major approach takes us from the vastness of intergalactic space to the very beginning of everything by studying the oldest light in existence, the cosmic microwave background, or CMB. This is the remnant glow from the Big Bang, a faint microwave static that fills every corner of the universe, a snapshot of the cosmos when it was just 380,000 years old. At that moment, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This light has been traveling ever since, and it carries with it an imprint of the universe's infant structure. The CMB is not perfectly uniform. It's like a cosmic fingerprint with tiny variations in temperature hotspots and cold spots that differ by mere millionths of a degree. These minute fluctuations are the seeds of all future structure, the blueprint for galaxies and clusters, and the pattern of these spots is exquisitely sensitive to the universe's ingredients, including dark matter. In the early universe, normal matter was a hot, ionized plasma coupled tightly with radiation. This created a pressure that resisted gravity, preventing matter from clumping easily. Dark matter, however, was immune to this pressure. It was free to start collapsing under its own gravity right away. The gravitational pull from these early dark matter clumps amplified the tiny ripples in the normal matter, making the hot spots slightly hotter and the cold spots slightly colder in a very specific pattern. When satellites like Planck map the CMB with incredible precision, the statistical pattern of these temperature variations they observe can only be explained if dark matter makes up about 27% of the universe. The CMB is a cosmic recipe, and it tells us in no uncertain terms that dark matter was a crucial ingredient from the very first moments. The third line of attack is the most direct and, in some ways, the most challenging. While astronomers map dark matter's gravitational effects on cosmic scales, particle physicists are trying to catch an individual particle of it here on Earth. These are the direct detection experiments, and they operate on the frontier of sensitivity. The idea is straightforward in principle. If our galaxy is swimming in a vast halo of dark matter particles, then countless trillions of them should be streaming through the Earth and through our bodies every single second. Very, very rarely, one of these particles might just bump into the nucleus of a normal atom. The goal is to build a detector so sensitive that it can register that tiny, almost imperceptible bump. To do this, scientists have had to create the quietest places on Earth. These laboratories are buried deep underground, in old mines or beneath mountains, shielded by a mile of solid rock from the constant barrage of cosmic rays that would otherwise overwhelm any signal. Inside, they house ultra-pure vats of detector material, often liquid xenon or germanium crystals, kept at cryogenic temperatures just a fraction of a degree above absolute zero. The entire apparatus is surrounded by layers of shielding to block natural radioactivity from the surrounding rock. They then wait, listening for the telltale flash of light or the minute amount of heat that would be released if a dark matter particle ever collided with an atomic nucleus in the detector. It is an exercise in supreme patience and engineering, trying to hear a whisper in a hurricane. So far, these experiments have not registered a confirmed, definitive signal. But their silence is not a failure. Every time an experiment like LUX Zeppelin or Xeno NNT reports a new, more sensitive null result, it tells us what dark matter is not. It rules out entire classes of theoretical particles, narrowing the search and guiding theorists toward new, more creative ideas. This quiet, persistent hunt in the darkness is a testament to human ingenuity and our unwavering determination to meet the unknown on its own terms. To truly grasp the power of this evidence, we need to take a short journey into the familiar territory of our own solar system. Picture the Sun at the center, with its family of planets orbiting around it, all held in place by its powerful gravity. Now think about their speeds. Mercury, the innermost planet, zips around the Sun at a blistering pace, completing an orbit in just 88 days. Earth, farther out, moves at a more moderate speed, taking a full year, and distant, icy Pluto, it ambles along in a slow, stately dance that takes 248 years. This pattern is not random. It is a direct consequence of Kepler's laws and Newtonian gravity. The Sun's gravitational grip weakens with distance, so objects farther out naturally feel a weaker pull and must move more slowly to maintain a stable orbit. It is a beautiful, predictable celestial dance, and for centuries, astronomers assumed that galaxies, being vast collections of stars, would behave in a very similar way. They expected that stars closer to the bright, dense core of a spiral galaxy would orbit very quickly, while those out in the dim, sparse outskirts would be moving much more slowly, just like the outer planets in our solar system. This was the logical prediction, the model that made perfect sense. What Vera Rubin and her colleague Kent Ford found when they meticulously measured the light from these distant galaxies shattered that expectation completely. Using a sophisticated spectrometer, they could measure the Doppler shift of starlight at different distances from a galaxy's center. This allowed them to calculate the orbital velocity of stars with remarkable precision. They weren't just looking at a few points, they were tracing the speed of stars from the brilliant inner bulge all the way out to the faint, wispy edges of the galactic disk. And the data they collected told a story that defied all conventional wisdom. The rotation curves were flat. This means that a star located tens of thousands of light years from the center, in the relative emptiness of the galactic hinterlands, was orbiting at virtually the same high speed as a star much closer in, right where most of the visible mass was concentrated. It was as if every planet in our solar system, from Mercury to Pluto, suddenly decided to race around the Sun at the exact same breakneck velocity. From a gravitational standpoint, this was impossible. A galaxy is not a solid disk like a vinyl record. It is a collection of individual stars, each orbiting independently. For those outer stars to be moving so fast, something extra had to be holding onto them, something with a tremendous amount of gravity that we simply could not see. The only plausible explanation was the presence of a massive, invisible halo of dark matter enveloping the entire visible galaxy. Think of a spiral galaxy not as an isolated island of stars, but as a brilliant city of light built at the center of an immense, invisible mountain. The stars we see are the city's lights, concentrated in the downtown core and along the well-lit streets of the spiral arms. But the mountain itself, the vast, dark structure that provides the gravitational foundation, extends far, far beyond the last visible star. This dark matter halo provides the extra gravitational pull, the unseen hand that keeps those high-speed outer stars from being flung off into the void. The mathematics is inescapable. To explain the observed flat rotation curves, this dark halo must contain many times more mass than all the luminous stars, gas, and dust combined. In fact, for a typical spiral galaxy, the dark matter outweighs the normal matter by a factor of 5 to 10. This means that what we see when we gaze at a breathtaking image of a galaxy like Andromeda is less than 20% of its actual substance. The rest, the overwhelming majority of its mass, is this mysterious, invisible material whose presence we can only infer from the relentless, high-speed dance of the stars it holds in its grasp. This discovery did more than just confirm the existence of dark matter. It fundamentally rewrote our understanding of what a galaxy is. Before Rubin's work, galaxies were seen as largely self-gravitating systems of stars. After her meticulous observations, we were forced to accept that the luminous galaxy is just the tip of a colossal iceberg. The true galaxy, the gravitationally dominant entity, is this immense sphere of dark matter, with the sparkling disk of stars merely a decorative feature embedded within it. This gravitational signature, the flat rotation curve, has since been observed in countless spiral galaxies across the universe. It is a universal clue, a consistent fingerprint left by dark matter wherever we look. It tells us that this isn't a peculiarity of one or two galaxies. It is a fundamental feature of cosmic architecture. The stars are telling us a story through their motion, a story of an unseen giant whose shadow stretches across the cosmos, and Vera Rubin was one of the first to truly listen. While the motions of stars within galaxies gave us our first robust clues, another line of evidence emerged that allowed us to visualize the invisible in a far more dramatic way. This technique relies on one of the most profound predictions of Einstein's theory of general relativity, the idea that mass warps the very fabric of space and time. Imagine spacetime as a vast, taut rubber sheet. When you place a heavy object on it, like a bowling ball, it creates a deep depression. Now, if you roll a marble past the bowling ball, its straight path will curve inward, following the contour of the dip. In the cosmos, gravity does the exact same thing to light. A massive object like a galaxy cluster creates a tremendous gravitational well in space-time, and when light from a more distant object travels through this warped region, its path is bent. This phenomenon is known as gravitational lensing, and it acts as nature's own telescope, creating cosmic mirages that are both beautiful and incredibly informative. These lensing effects come in different forms, each revealing more about the hidden mass. In the most spectacular cases, known as strong lensing, the alignment is so perfect that we see multiple mirrored images of a single background galaxy, or its light is stretched into brilliant blue arcs of light that curve around the foreground cluster like a celestial halo. It's a breathtaking sight, a natural optical illusion on an unimaginable scale. But there's a more subtle and pervasive version of this effect called weak lensing. Here, the distortions are not dramatic enough to create obvious arcs or multiple images. Instead, the shapes of thousands of faint, distant galaxies are ever so slightly stretched and sheared, their oval shapes aligned in a coherent pattern that points toward the presence of the intervening dark matter. Individually, each distortion is tiny, but by statistically analyzing the shapes of millions of galaxies across a patch of sky, astronomers can create a detailed mass map, essentially charting the gravitational landscape of the invisible dark matter that litters the cosmos. It's like looking at the reflections in a funhouse mirror and being able to calculate the exact shape of the warped glass that's causing the distortion. Perhaps the most iconic and powerful example of this technique in action is a system known as the bullet cluster. This is not a single galaxy, but a pair of massive galaxy clusters that have recently collided and passed right through each other. This cosmic collision provides a perfect natural experiment to separate the different components of matter. Think of it like this: when two clouds of smoke collide, they mix and swirl together. But if you throw two handfuls of rocks through the smoke, the rocks will pass right through with little interaction, ending up in a different place than the mingled smoke. In the bullet cluster, the normal baryonic matter is like the smoke. This matter, mostly in the form of superheated gas that glows in X-rays, did interact during the collision. The gas clouds slammed into each other, creating immense friction and heat, and they slowed down, ending up in the central region between the two clusters. However, the dark matter is like the rocks, because it doesn't interact with itself or the gas through any force except gravity. It was effectively frictionless. The dark matter from both clusters simply passed right through the collision without slowing down. This is where gravitational lensing provides the stunning proof. When astronomers used the weak lensing technique to map the total mass distribution of the bullet cluster, they found two distinct peaks of mass. These peaks did not align with the glowing clouds of hot gas in the center. Instead, they were located where the visible galaxies of each cluster were, having passed through just like the dark matter. The inescapable conclusion is that most of the mass in the system is not in the gas, but in these separate, invisible halos. The bullet cluster gives us a direct visual testament that dark matter is real. It is distinct from normal matter, and it behaves as a collisionless substance. This is evidence that is incredibly difficult to explain away with modified theories of gravity, because what you have is a clear separation between what creates the gravity, the lensing mass, and what constitutes the majority of the normal matter, the X-ray gas. It's as if we are seeing the shadow of the invisible giant cast upon the sky, a shadow that has physically stepped away from the visible world. Gravitational lensing, therefore, does more than just confirm the presence of dark matter. It allows us to trace its distribution with precision, painting a picture of the cosmic skeleton that holds our universe together, a skeleton we now know moves to its own silent, invisible rhythm. While the movements of galaxies and the bending of light give us powerful clues from the relatively recent universe, perhaps the most profound and universal evidence for dark matter comes from a fossilized whisper of light from the very dawn of time itself. This evidence is imprinted on the cosmic microwave background, the CMB, and it serves as the ultimate cosmic recipe, a set of ingredients so precise that it leaves no room for doubt about the existence of this mysterious substance. To understand why, we need to travel back to a time when the universe was not a vast, dark expanse, but a searing, opaque fireball. In its earliest moments, the cosmos was so hot and dense that it was a plasma of protons, electrons, and photons, all bouncing off each other in a chaotic, blinding fog. Light couldn't travel freely. It would instantly be scattered by a free electron trapped in a constant, violent dance. This all changed about 380,000 years after the Big Bang. The universe had expanded and cooled just enough for a monumental event to occur, an event cosmologists call recombination. In this pivotal moment, the free electrons and protons were finally moving slowly enough to combine and form the first stable hydrogen atoms. For the very first time, the universe became transparent. The photons, which had been trapped in the hot plasma, were suddenly set free. This first flash of liberated light is what we detect today as the cosmic microwave background. It is the oldest picture we can ever take of our universe, a baby photo from its infancy, and it fills every cubic centimeter of space around us. Wherever you are right now, trillions of these primordial photons are passing through your body every second, a constant rain of ancient light from the moment of creation. If our eyes could see microwaves, the entire night sky would glow with a uniform, dull light. But when scientists built incredibly sensitive instruments, like the Planck and WMAP satellites, and mapped this radiation with exquisite precision, they discovered it was not perfectly uniform. It is imprinted with an intricate pattern of tiny temperature variations, minute hot spots and cold spots that differ by only about 100,000th of a degree. These fluctuations are not random noise. They are the cosmic seeds from which the entire large-scale structure of the universe would eventually grow. The slightly denser, hotter spots are the regions where matter had begun to clump together under gravity, and it is in the specific statistical pattern of these spots, what scientists call the power spectrum, that the fingerprints of dark matter are indelibly pressed. The story of how dark matter left its mark is a tale of two types of matter behaving completely differently in the early universe. In that hot, dense plasma, the normal baryonic matter, the stuff we're made of, was tightly coupled to the radiation. Imagine it as a thick soup where the light itself created an immense outward pressure, like the steam in a pressure cooker, pushing back against gravity and preventing the matter from collapsing easily. It was constantly being buffeted and smoothed out. Dark matter, however, was the silent, stoic presence in the background. Because it doesn't interact with light at all, it was completely immune to this radiation pressure. From the very first moments, dark matter could feel only gravity. This meant that while the normal matter was sloshing back and forth, held in place by the intense radiation, the dark matter was free to start clumping together right away. These early dark matter clumps, these gravitational potholes, began to form a subtle landscape across the young cosmos. their gravitational pull started to work on the normal matter. As the universe expanded and cooled toward the moment of recombination, the normal matter felt the tug of these pre-existing dark matter overdensities. The baryons began to flow toward the gravitational wells carved out by the dark matter, amplifying the tiny initial ripples. This process left a specific signature in the CMB. The hot spots are a little bit hotter because the normal matter, falling into the dark matter wells, got compressed and heated by the radiation it was still coupled to. The statistical size and distribution of these spots, the precise way they are scattered across the sky, acts like a cosmic barcode. When scientists scan this barcode with the predictions of their theoretical models, the result is unequivocal. The pattern we observe can only be replicated if about 27% of the universe's composition is made of cold, collisionless dark matter. No other ingredient, no tweak to the laws of gravity, can reproduce the exquisite detail of the CMB power spectrum. It is the most stringent and precise measurement we have, a universal mandate for the existence of dark matter. The importance of this cannot be overstated. The CMB tells us that dark matter was not some later addition to the cosmos. It was a fundamental architect from the very beginning. It provided the essential gravitational scaffolding that allowed structure to form in the time available. Without dark matter's head start, the gentle ripples in the normal matter would have been far too weak to collapse into the first stars and galaxies within billions of years. The universe would have remained a much smoother, darker, and emptier place. The magnificent cosmic web of galaxies, the brilliant clusters, and the vast voids we see today all trace their lineage back to those subtle gravitational seeds laid down by dark matter and permanently recorded in the frozen light of the cosmic microwave background. This fossilized afterglow is therefore more than just a picture. It is the foundational document of our cosmos, and it states in no uncertain terms that the universe we see is built upon a hidden framework of darkness. So we know dark matter is out there, its gravitational pull shaping the cosmos, but the billion-dollar question remains, what is it actually made of? If it's a particle and not some modification to gravity, then it must be a fundamentally new type of particle, one that lies completely outside the standard model of particle physics, the otherwise triumphant catalogue of every known fundamental building block of the visible universe. This is the heart of the particle hunt, a grand, global scientific endeavor to identify the fundamental constituent of the cosmic dark side. For decades, one particular class of hypothetical particle has dominated the conversation, a candidate so elegant that physicists dubbed its emergence the WIMP miracle. WIMP stands for Weakly Interacting Massive Particle, and the name itself is a perfect description of its proposed properties. It would have mass, so it feels and exerts gravity, and it would interact with normal matter only through the weak nuclear force, the same force responsible for radioactive decay. This feeble interaction is the key. It explains why these particles are so fantastically elusive, streaming through our planet and our bodies by the trillions every second without a trace. The miracle part is what makes this idea so compelling to physicists. When theorists calculated what would have happened in the hot, dense early universe, they found that if a stable particle with weak scale interactions and a mass about 100 times that of a proton did exist, it would have been produced in copious amounts during the Big Bang. As the universe expanded and cooled, these particles would have annihilated each other when they collided, but the expansion would have diluted their density, eventually freezing them out and leaving behind a specific relic abundance. The stunning coincidence is that the calculated density of these frozen-out WIMP matches almost perfectly the observed density of dark matter in the universe today. It's as if the universe left a clue in its own initial conditions. a cosmic breadcrumb that points directly to this specific kind of particle. This elegant theoretical prediction has driven a multi-decade, multi-million-dollar experimental quest to find one. These direct detection experiments are feats of extraordinary engineering and patience. They are essentially ultra-sensitive listening posts buried deep underground, in places like the Sanford Underground Research Facility in South Dakota or beneath the Gran Sasso Mountain in Italy. The depth, often over a mile of rock, is crucial to shield the detectors from the constant cosmic ray shower that would otherwise create an impenetrable background noise. At the heart of these experiments are vast vats of ultra-pure liquid xenon, cooled to extremely low temperatures. The idea is starkly simple. Wait for a WIMP from our galaxy's dark matter halo to, by sheer chance, bump into the nucleus of a xenon atom. Such a collision would produce a tiny flash of light and a wisp of electrical charge, signals so faint they are at the very edge of what is technologically possible to measure. Experiments like LUX Zeppelin and Xeno NNT represent the cutting edge of this search, with ever larger tanks of xenon and ever more sensitive photodetectors, all operating in a pristine, radioactively clean environment. They are trying to catch the faintest whisper of a collision, a single, quiet click in the profound silence of the underground, a click that would revolutionize our understanding of the universe. Yet, despite decades of searching and detectors that have grown exponentially in sensitivity, the WIMP have not shown themselves. The persistent silence from these exquisitely tuned machines has begun to cast a long shadow over the once bright prospects of the WIMP miracle. This has forced physicists to broaden their horizons and consider a much wider and more exotic zoo of potential dark matter candidates. One of the most compelling alternatives is the action, a particle that is in almost every way the opposite of a WIMP. Where a WIMP is heavy, the action is phenomenally light, potentially billions of times lighter than an electron. It was originally proposed not to explain dark matter, but to solve a deep and esoteric problem in particle physics known as the strong CP problem, which deals with the surprising symmetry in the behavior of the strong nuclear force. It was later realized that if actions did exist, they would have been produced in vast numbers in the early universe and could very naturally account for the dark matter we observe. The hunt for actions is a completely different kind of scientific pursuit because they are so light and theoretically interact with electromagnetic fields. The strategy is not to wait for a nuclear collision, but to try and convert them into something we can easily detect, photons of light. Experiments like the Action Dark Matter E-experiment, or ADMX, are essentially the most sensitive radio receivers ever built. They use a powerful superconducting magnet to create a strong magnetic field inside a resonant cavity. The theory suggests that an action passing through this magnetic field could, under the right conditions, convert into a microwave photon. The experiment then tunes the cavity, much like tuning an old-fashioned radio, searching for a specific, faint frequency among all the cosmic static. It's a painstaking process, listening for a specific, pure note in a cosmic symphony of noise, a note that would signal the presence of a universe-filling sea of these ghostly, ultra-light particles. The sheer diversity of candidates now on the table is a true reflection of our profound uncertainty. Beyond WIMP and actions, theorists have proposed a wild menagerie of possibilities. There are sterile neutrinos, which are heavier, right-handed cousins of the known neutrinos. There are WIMPs, monstrously heavy particles that would have formed right after the Big Bang. There are even ideas involving tiny primordial black holes formed in the universe's first second, or particles that live in extra-spatial dimensions beyond the three we experience. This expansive and creative search is a testament to the scientific drive to understand nature, No matter how well it hides its secrets, the particle hunt is a high-stakes endeavor, one that pits human ingenuity against the deepest mysteries of the cosmos. Every null result, every silent detector, is not a failure but a step forward, telling us which paths are dead ends and forcing us to think more creatively about what the universe is truly made of. Imagine trying to hear a single, quiet pin drop in the middle of a roaring heavy metal concert. That is the monumental challenge facing the scientists who operate direct detection experiments. Their goal is audacious: to record the infinitesimal vibration, the faintest whisper of heat or light, that would be produced if a single particle of dark matter, after streaming across the galaxy for billions of years, finally bumps into the nucleus of an ordinary atom here on Earth. The entire endeavor is an exercise in extreme isolation and precision, a hunt for a ghost in a universe filled with constant, deafening noise. To even have a chance, these researchers must create the quietest places on the planet, environments so pristine and shielded that they push the very limits of technology. This is not astronomy with telescopes. This is a deeply intimate form of particle physics, a direct attempt to touch the untouchable. The first and most critical step in this quest is to escape the cacophony of everyday life at the surface. Our planet is constantly bombarded by a rain of cosmic rays, high-energy particles from deep space that slam into the atmosphere, creating a shower of secondary particles that would completely overwhelm any potential dark matter signal. To escape this relentless downpour, scientists go deep, very deep. They build their laboratories a mile or more underground, in places like the Sanford Underground Research Facility in a former South Dakota gold mine, or beneath the Gran Sasso Mountain in Italy. Here, the solid rock overhead acts as a colossal shield, absorbing nearly all of that cosmic interference. The silence underground is profound, not just in terms of sound, but in terms of particle physics. It is a sanctuary where the faintest of signals might finally be heard. But the challenges don't end there. The very rocks that provide shielding are themselves slightly radioactive, and even the cleanest materials we can manufacture contain trace amounts of radioactive isotopes. So, within these cavernous underground halls, the detectors themselves are nested inside a Russian doll of additional shielding layers of lead, copper, and pure water, each one designed to block out a different type of background radiation. The goal is to create a bubble of near-perfect stillness, a volume of space where any tiny disturbance has a chance of being something extraordinary. At the heart of these experiments lies the detector itself, a masterpiece of engineering and material science. The most sensitive of these use vast quantities of ultra-pure liquid xenon, a noble gas that is exceptionally clean and responsive. In experiments like LUX Zeppelin or Xeno NNT, several tons of xenon are kept in a massive stainless steel tank, cooled to cryogenic temperatures to keep it liquid. The xenon is so pure that it has been meticulously filtered to remove even a single atom of a radioactive contaminant like krypton-85 for every trillion atoms of xenon. This level of purity is almost unimaginable. When a particle interacts within this liquid xenon, it can produce two signals: an immediate flash of light, called a scintillation signal, and a subsequent pulse of electrical charge. An array of exquisitely sensitive light sensors, known as photomultiplier tubes, lines the top and bottom of the tank, waiting to capture that initial flash of photons. An electric field is then applied to drift the freed electrons upward, where they produce a second, smaller flash of light upon extraction. By comparing the timing and the size of these two light signals, physicists can pinpoint the location of the interaction within the tank and, crucially, determine whether it was likely caused by the gentle recoil of a nuclear nucleus. the signature of a heavy dark matter particle like a WIMP, or the sharper recoil of an electron, which is typically background radiation. This two-phase design allows the experiment to act as its own watchdog, helping to distinguish a potential dark matter candidate from mundane imposters. Despite these heroic efforts spanning decades and involving hundreds of the world's brightest minds, a definitive, reproducible signal has remained elusive. The detectors have grown larger and more sensitive with each new generation, moving from kilograms to tons of xenon. They have pushed the limits of what is possible, setting ever more stringent constraints on how strongly dark matter can possibly interact with normal matter. And yet the silence persists. It would be easy to see this as a failure, a story of disappointment, but in science, a null result is not a dead end, it is a signpost. This profound quiet is in its own way incredibly informative. It tells us with great certainty what dark matter is not. It has ruled out vast swaths of the theoretical territory once occupied by the most popular dark matter candidates, particularly the simpler models of WIMP. Each time a new experiment reports its results and finds only background noise, it forces theorists to go back to their chalkboards. They must now dream up more exotic, more subtle possibilities, particles that are lighter, or that interact through even feebler forces, or that possess properties we haven't even considered. The search has become a dialogue between theory and experiment, where the silence of the detectors asks ever more pointed questions about the true nature of the cosmic dark side. This quiet, persistent search, conducted in the profound darkness of underground laboratories, is one of the great testaments to human curiosity and perseverance. It is a venture that offers no guarantee of success, driven purely by the desire to understand the fundamental makeup of our universe. The scientists involved know they are searching for a needle in a cosmic haystack, a needle that may not even be there in the form they expect. Yet they continue to build ever more sensitive ears, listening intently in the hope that one day, in the deepest quiet we can create, they will finally hear the long-awaited whisper from the dark. But if listening for dark matter in the quiet of an underground mine has proven fruitless, what if we could instead force it to reveal itself in the most violent, energetic collisions humanity can possibly produce? This is the brilliant logic behind the third great pillar of the hunt, a strategy that takes us from the deep silence of subterranean labs to the roaring, controlled chaos of the world's largest machine, the Large Hadron Collider at CERN. Nestled in a circular tunnel 17 miles in circumference beneath the border of Switzerland and France, the LHC is a cathedral of particle physics. Its sole purpose is to accelerate protons to velocities within a whisper of the speed of light, and then smash them together head-on, recreating, for a fleeting fraction of a second, the conditions of the universe a trillionth of a second after the Big Bang. In these microscopic fireballs, temperatures and energies soar to levels not seen since the dawn of time, and the hope is that in this primordial forge, we can literally create dark matter from pure energy. The strategy is as ingenious as it is indirect. Scientists aren't trying to see the dark matter particle itself. That would be impossible given its ghostly nature. Instead, they are looking for its shadow, for the ghostly imprint it leaves by its absence. The principle rests on one of the most sacred laws in all of physics, the conservation of energy and momentum. In any collision inside the LHC's massive detectors like ATLAS or CMS, physicists can account for the energy and direction, the momentum of every single particle that comes flying out of the wreckage. They know precisely how much energy went into the collision, and they can measure with incredible precision how much energy comes out in the form of familiar particles like photons, electrons, and quarks. If, after a spectacular collision, the accountants of energy find that there is a significant shortfall, a chunk of momentum that seems to have simply vanished into thin air, that is the telltale signature they are desperate to find. This missing energy would be the smoking gun, the clear indicator that something invisible and non-interacting was created in the collision and then sailed right through the multi-layered detector without a trace, carrying its energy and momentum away with it. It would be like watching a bank heist on a security camera where you see the thieves run in, hear the explosion, and then see nothing come out, yet the money is gone. The only explanation is that they left by a hidden, invisible tunnel. In the LHC, that invisible tunnel is a dark matter particle. This approach represents a breathtaking synergy between the science of the unimaginably large and the infinitesimally small. Cosmologists who study the grand structure of the universe provide the target. They tell us how much dark matter must exist. Particle physicists who study the fundamental constituents of reality then use their colossal machine to try and create it, probing the laws that governed its birth in the first moments of the cosmos. It is a beautiful convergence where understanding the gravity of galaxy clusters directly informs the operation of a machine that studies the quantum world. The LHC has already proven its revolutionary power with the discovery of the Higgs boson in 2012, a particle that confirms our understanding of how all other particles get their mass. That discovery filled in the last missing piece of the Standard Model, the wildly successful theory of the known particles and forces, but the Standard Model has no room for dark matter. Finding it at the LHC would therefore be an even more profound discovery, flinging open the door to a whole new world of physics, a hidden sector of particles and forces that have shaped the cosmos in secret for billions of years. So far, however, the dark matter particle has remained stubbornly elusive, even to the mighty LHC. After years of collecting data from billions upon billions of these high-energy collisions, no clear, unambiguous signal of significant missing energy has emerged. But just like the silent underground detectors, this null result is far from a failure. Every collision that does not produce a dramatic energy imbalance tells us something. It allows physicists to rule out specific theoretical models, particularly certain versions of the popular supersymmetry theory, which posits that every known particle has a heavier, super partner, the lightest of which could be a perfect dark matter candidate. The LHC has systematically pushed the possible mass range for such particles to higher and higher energies, telling us that if dark matter is a WIMP, it must be heavier or interact even more weakly than we had hoped. This process of elimination is a crucial part of the scientific journey, narrowing the path forward and forcing theorists to be ever more creative. The ambition to create the universe's own darkness in a laboratory is one of the boldest endeavors in modern science, a testament to our refusal to be passive observers of the cosmos. We are not just waiting for a ghost to whisper, we are trying to conjure it in a storm of our own making, hoping that in the flash of a man-made Big Bang, the dark universe will finally be forced to show its hand. While we dig deep underground and smash particles together in colossal colliders, another group of intrepid explorers is taking a completely different approach, turning our most powerful telescopes towards the sky not to look at the light, but to listen for the echoes of destruction. This is the world of astrophysical probes, a strategy that searches for the faint, secondary signals produced when dark matter, in the vastness of space, decides to reveal itself by its own hand. The logic here is beautifully indirect. We may not be able to see the dark matter particle itself, but if it ever interacts with itself, it might leave behind a cosmic calling card in a form that we can detect. Imagine two ghosts invisible to everyone colliding in a dark room. You might not see the ghosts, but if that collision produces a shattering of glass or a flash of light, you would know without a doubt that something was there. Astrophysicists are essentially trying to be the cosmic listeners for that shattering glass. One of the most compelling ideas in this realm is the possibility that dark matter particles are their own antiparticles. In the world of normal matter, every particle has an opposite counterpart, an antiparticle. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy, converting their mass into other forms of radiation according to Einstein's famous equation, E equals mc². For example, an electron colliding with a positron, its antimatter twin, will annihilate to produce gamma-ray photons. Now, if a dark matter particle were its own antiparticle, then whenever two of them collided, they would also annihilate. Their immense mass would be transformed into a burst of energy, creating a shower of familiar, standard model particles that we know how to detect. This process would produce a unique and potentially identifiable signal, an excess of gamma rays, neutrinos, or positrons streaming from regions of space that are absolutely packed with dark matter. We wouldn't be seeing the dark matter, we would be seeing the fiery aftermath of its mutual destruction. This is where the hunt becomes a cosmic treasure map. To find these signals, scientists know exactly where to look, the places where the dark matter is most densely concentrated, creating the highest probability for these rare annihilation events to occur. The most promising hunting grounds are the hearts of galaxies, particularly our own Milky Way. At the very center of our galaxy, theorists believe there sits a supermassive black hole, and surrounding it, an incredibly dense spherical halo of dark matter, a region where the particles would be swarming in unimaginable numbers. If annihilations are happening anywhere, they should be happening there at a potentially detectable rate. Another prime target are dwarf spheroidal galaxies. These are small, faint satellites of the Milky Way that are, fascinatingly, made almost entirely of dark matter. They have very few stars and very little gas, meaning their mass-to-light ratio is enormous. They are essentially pristine, floating balls of dark matter, making them perfect, clean laboratories. If you see a spike of gamma rays coming from one of these otherwise quiet, dark-dominated dwarfs, it's a very strong hint that you found something profound. To conduct this search, astronomers use space-based observatories like the Fermi Gamma Ray Space Telescope, which has been scanning the entire sky for over a decade, meticulously cataloging the sources of high-energy gamma-ray radiation. The Fermi team pores over this colossal dataset, looking for any unexplained excess of gamma rays emanating from the galactic center or from known dwarf galaxies. They must perform a delicate balancing act, carefully subtracting all the known astrophysical sources of gamma rays, pulsars, supernova remnants, and active galactic nuclei to see if a faint, diffuse glow of annihilation radiation remains. It's like trying to hear a single, pure note from a violin that is playing in the middle of a roaring heavy metal concert. The data has shown some intriguing, unexplained excesses of gamma rays from the galactic center, a signal that has sparked thousands of scientific papers and fierce debate. Is it the long-sought signature of dark matter annihilation, or is it something more mundane, like a previously unknown population of pulsars? The answer remains elusive, but the search continues with relentless precision. Annihilation isn't the only way dark matter might betray its presence. Another tantalizing possibility is that dark matter particles are not perfectly stable. What if, over the immense timescales of the universe, they slowly, quietly decay? In this scenario, a single dark matter particle could spontaneously transform into lighter, more familiar particles, emitting a faint but steady stream of radiation in the process. This would be a much quieter signal than the violent burst of an annihilation, more like a constant, universal whisper than a sudden shout. The energy of this decay radiation would be very specific, tied directly to the mass of the dark matter particle itself. If we could pinpoint this telltale energy signature across the sky, it would be like finding the fossilized fingerprint of the particle. Scientists search for this by looking at the diffuse X-ray and gamma-ray background, the all-sky glow that remains after all the bright, discrete sources have been removed. They search for a faint, monochromatic line, a spike at one specific energy that has no other astrophysical explanation. Finding such a line would be a smoking gun, a direct measurement of the dark matter particle's mass and a first glimpse into its hidden physics. This entire approach, listening for the echoes of annihilation or the faint hum of decay, represents a fundamental shift in how we do astronomy. For centuries, we have studied the universe by collecting the light that objects emit or reflect. But here, we are not studying light. We are studying the secondary byproducts of something that is utterly, fundamentally dark. We are trying to map an invisible world by the subtle ripples it creates in the visible one. It is astronomy of the completely unseen, a detective story where the clues are not footprints in the sand, but phantom energies from the void. Every unexplained gamma ray, every anomalous neutrino, carries with it the potential to be the message we have been waiting for, a signal from the dark universe telling us at long last what it is made of. For all its remarkable success in explaining the grand architecture of the cosmos, the dark matter story is not without its own intriguing plot twists. When we zoom in from the vast cosmic web to focus on the intricate details of individual galaxies, we encounter a series of puzzles that reveal our model is not yet complete. These are the small-scale problems of cosmology, and they act like subtle cracks in a beautiful, well-established theory, hinting that there might be more to the dark universe than we currently understand. The overarching framework of cold dark matter is so powerfully supported by the large-scale structure of the universe and the cosmic microwave background that these smaller issues don't threaten to topple it. Instead, they serve as crucial guides, pointing scientists toward a more nuanced and detailed picture of how dark matter truly behaves. It's a reminder that even our most successful scientific theories are works in progress, constantly being refined and improved by confronting them with nature's most stubborn details. One of the most persistent of these puzzles is known as the Core-Cusp problem. According to the most straightforward computer simulations of how cold dark matter should collapse under its own gravity, the density of a dark matter halo should increase dramatically toward the center of a galaxy. Imagine a steep, densely packed mountain peak, a cusp where dark matter particles swarm in incredible numbers at the very heart of the galaxy. This is what the pristine theory, focusing only on gravity, predicts. However, when astronomers study the motions of stars and gas within certain dwarf galaxies, small, faint galaxies that orbit larger ones like the Milky Way, they find something quite different. The data suggests that many of these galaxies have a core, a central region where the dark matter density is much more constant, like a flattened hilltop rather than a sharp peak. It's as if something has been stirring the pot in the galactic center, preventing the dark matter from piling up in the way our simulations insist it should. This discrepancy between the predicted cusp and the observed core is a major headache for cosmologists, a clear sign that the simple, gravity-only picture of dark matter might be missing a key ingredient. A second, equally famous conundrum is the missing satellites problem. Our most sophisticated simulations of cosmic structure formation, which model the evolution of dark matter from the early universe to the present day, paint a very specific picture of what a galaxy like our Milky Way should look like. They predict that our galaxy should be surrounded by a vast swarm of thousands of small dark matter clumps, or subhalos. Each of these subhalos has the potential to host a small, faint dwarf galaxy. Yet, when we actually count the number of satellite galaxies orbiting the Milky Way, we find only a few dozen. It's a dramatic mismatch. The simulations predict a bustling metropolis of dark matter satellites, but our telescopes reveal only a quiet suburban neighborhood. For a long time, it was thought that perhaps the smallest clumps simply never managed to form stars, remaining completely dark and invisible. While this is certainly true for some, it doesn't fully resolve the tension. The problem forced astronomers to look harder, and with more powerful telescopes, they have indeed discovered many more ultra-faint dwarf galaxies than were known before. But the count still falls far short of the teeming population predicted by the simplest models, keeping this puzzle very much alive. So, what could be causing these curious discrepancies? Scientists are exploring several fascinating possibilities, each pushing the boundaries of our understanding. One compelling idea is that our assumption that dark matter is cold and perfectly collisionless might be just a little too simple. Perhaps dark matter has a more complex personality. For instance, it could be warm. Warm dark matter would consist of particles that move at a significant fraction of the speed of light in the early universe. This extra speed would have a smearing effect, preventing dark matter from collapsing into the very smallest clumps. This would naturally explain the missing satellites problem, as the smallest subhalos would never form in the first place. However, warm dark matter can struggle to explain the Core-Cusp problem and might create issues for the formation of the first galaxies. Another intriguing proposal is that dark matter might be self-interacting. In our standard model, dark matter particles pass right through each other like ghosts, but what if they could, very rarely, bounce off one another? This self-interaction would act as a form of friction. In the dense center of a galaxy where particles are crowded together, these occasional collisions would transfer energy from the inner, high-density regions to the outer parts, effectively heating up the core and smoothing out the sharp cusp into a gentler core. It's a beautifully elegant solution that directly addresses one of the key problems. Alternatively, the solution might not lie with dark matter at all, but with the ordinary matter we thought we understood better. The complex physics of star formation and the tremendous energy released by supernova explosions can drive powerful winds that push gas out of the center of a galaxy. This outflowing gas, driven by normal matter, could dynamically drag on the dark matter gravitational potential, slowly carving out a core over billions of years. The true answer may well be a combination of these effects, a more complex dance between dark and normal matter than we first imagined. These small-scale problems are not signs of a theory in crisis, but rather the hallmark of a healthy, active field of science. They represent the cutting edge of research, the places where our fundamental model is being stress-tested by precise new data. Just as tiny anomalies in the orbit of Mercury in the 19th century hinted at the need for Einstein's theory of general relativity, these puzzles in galactic dynamics are guiding us toward a more complete and sophisticated understanding of dark matter. They force us to ask deeper questions. Is dark matter simple, or does it have a rich, hidden physics of its own? How exactly does it couple with the violent, energetic processes of star formation and stellar death? By grappling with the Core-Cusp problem and the missing satellites problem, cosmologists are not abandoning the dark matter paradigm. They are refining it, adding new layers of complexity to a story that is still being written. These mysteries remind us that the universe is always more subtle and surprising than our best models, and that the greatest discoveries often lie in the details that don't quite fit. For generations, the scientific method has operated on a powerful principle. When observations don't match predictions, you don't discard the observations, you search for what's missing. This has been the guiding logic behind the dark matter quest, the conviction that an unseen form of matter must be the invisible actor causing the gravitational anomalies we see. But what if, for all this time, we've been following the wrong path? What if the problem isn't with what's out there in the cosmos, but with the very laws of physics we hold so dear here on Earth? This is the radical, compelling, and fiercely debated proposition at the heart of an alternative approach. Instead of inventing a new substance to fill the gaps, perhaps we should be rewriting the rules of gravity itself. It's a philosophical split that strikes at the core of how we understand the universe. Do we live in a cosmos dominated by darkness we cannot see, or have we simply been misreading the gravitational script all along? The most prominent and resilient of these alternative theories is known as MUND, which stands for Modified Newtonian Dynamics, first proposed by Israeli physicist Mordechai Milgrom in the early 1980s. MUND is built on a beautifully simple yet profound idea. Milgrom noticed that the discrepancies in galaxy rotation curves all seem to kick in at a specific threshold, not at a certain distance from the galactic center, but at a very specific, incredibly low level of acceleration. In the inner regions of galaxies where gravity is strong, Newton's and Einstein's laws work perfectly. But out in the far outskirts, where a star feels only the faintest gravitational tug, something changes. MUND proposes a simple modification. It suggests that at these exceptionally low accelerations, the force of gravity stops following the familiar inverse square law and instead falls off more slowly. This tiny tweak to the mathematics of motion has a dramatic effect. When you apply MUND formula to a spiral galaxy, the predicted rotation curve naturally becomes flat, perfectly matching the observations made by Vera, Rubin, and others, all without needing a single particle of dark matter. It's an elegant solution that seems to solve the problem with a stroke of a pen, not a particle detector. The appeal of MUND is undeniable. For individual galaxies, it works remarkably well, often providing a better fit to the rotation curve data than some dark matter models. Proponents of the theory argue that it is a more parsimonious explanation. It solves the mystery without invoking a vast, invisible universe of unknown particles that have evaded detection for decades. They see dark matter as a complicated, ad hoc solution, while MUND appears as a simple, if revolutionary, adjustment to a known law. This philosophical stance is powerful. Why invent a whole new cosmology of dark matter and all the complex astrophysics that comes with it, when a minor modification to gravity can explain the observations so neatly? For a time, it seemed like MUND might just be the paradigm shift physics needed, a way to clear away the cosmic ghosts and explain the universe with the physics we already know. However, as science always demands, a good theory must do more than explain one set of data. It must account for all the evidence, and this is where MUND begins to encounter formidable challenges. Its most significant struggles emerge when we leave the relatively simple realm of isolated spiral galaxies and look at the more complex and violent environments of galaxy clusters. The bullet cluster, which we discussed earlier, stands as a towering monument in this debate. You'll recall that in this colliding cluster system, the gravitational lensing map revealed that the bulk of the mass was located away from the normal matter, the hot X-ray gas. For dark matter theory, this is a direct and visual proof. The collision separated the collisionless dark matter from the interacting normal matter. For MUND, the bullet cluster is a serious problem. If gravity is simply modified, then the mass should always be located exactly where the visible matter is. The fact that the gravity, as shown by the lensing, is in a completely different place than most of the atoms is incredibly difficult for any modified gravity theory to explain. WIMP proponents have attempted to add their own forms of unseen matter, like massive neutrino clouds, to bridge this gap, but these solutions often feel just as contrived as the dark matter they seek to replace, undermining the very simplicity that made WIMP attractive in the first place. The second, and perhaps even greater, hurdle for WIMP comes from the very beginning of time, imprinted on the cosmic microwave background. The precise pattern of hot and cold spots in this ancient light is a detailed record of the universe's infant structure, and it acts like a cosmic fingerprint. The standard model of cosmology, which includes both dark matter and dark energy, the lambda-CDM model, fits this fingerprint almost perfectly. The reason is deeply rooted in the physics of the early universe. Before the CMB was released, the normal matter was a plasma coupled tightly with radiation, creating immense pressure that prevented it from clumping effectively. Dark matter, unaffected by this radiation, was free to start collapsing early, creating the gravitational seeds for structure. The specific size and distribution of the hot spots we see in the CMB are a direct result of this interplay between the sluggish normal matter and the proactive dark matter. WIMP, in its original form, lacks this crucial component. It has no natural way to explain why these specific acoustic oscillations in the CMB look the way they do. Without a form of dark matter to provide the initial gravitational scaffolding, the universe, as predicted by a pure WIMP model, would not have formed the intricate cosmic web we observe, and the CMB would look radically different. To match the CMB data, WIMP would require such extensive modification and the addition of other unknown components that it begins to lose its elegant simplicity. This ongoing debate between dark matter and modified gravity is not a sign of a broken science. It is science at its absolute best. It represents the essential, dynamic process of competing ideas being forged in the fire of observational evidence. Proponents on both sides are forced to sharpen their arguments, refine their models, and confront their theories with every new piece of data that comes in. The dark matter camp must explain the persistent null results from direct detection experiments and the small-scale problems within galaxies. The WIMP camp must find a way to naturally explain the evidence from galaxy clusters and the CMB without resorting to increasingly complex add-ons. This tension is what drives progress. It forces everyone to think more deeply, to question their assumptions, and to seek out even more precise and decisive tests. It's a fundamental debate not just about what the universe is made of, but about the very nature of the forces that govern it. Are we on the verge of discovering a whole new world of particles, or are we about to witness the next great revolution in our understanding of gravity? A revolution that would shake the legacy of Newton and Einstein themselves? The answer remains one of the most thrilling and open questions in all of modern physics. So if dark matter is the invisible mountain providing the gravitational foundation for our cosmic cities, then dark energy is the strange, silent wind that is steadily and irrevocably blowing the entire landscape apart. We've already seen how its discovery shattered the paradigm of a slowing cosmic expansion, but to truly grasp its power, we need to understand that dark energy is not merely a component of the universe. It is the dominant component, the lead actor on the cosmic stage, and it is single-handedly writing the final chapter for everything that exists. Imagine the entire cosmos as a vast and intricate tapestry, woven from the threads of matter, energy, and space-time. For billions of years, the dominant force shaping this tapestry was gravity, an attractive force that worked to pull the threads closer together, weaving galaxies and clusters into an ever more complex structure. But about 5 billion years ago, a fundamental shift occurred. As the universe continued to expand, the density of matter, both dark and normal, diluted, its gravitational influence weakening with the growing void. Meanwhile, the energy density of dark energy, if it truly is a cosmological constant, remained well constant. In every cubic centimeter of new space that was created, the same amount of this repulsive energy appeared. As matter thinned out, dark energy's relentless push became the dominant force, and the universe's expansion switched from deceleration to acceleration. It was the moment the cosmic wind began to blow stronger than gravity's pull. This acceleration, if it continues unabated, leads to a future for our universe that is profoundly alien, and to our life-loving sensibilities deeply bleak. Cosmologists call this the Big Freeze or heat death. It's not a dramatic, fiery end like a big crunch, but a slow, cold, and lonely fading away. Picture our cosmic neighborhood today. We are part of the local group, a gravitationally bound family of galaxies including the Milky Way, Andromeda, and a few dozen smaller dwarfs. Because we are bound together, dark energy's expansive force cannot tear us apart. We are like a tight-knit village on a riverbank, safe from the rising current. But every other galaxy cluster beyond our local group is like a distant city on the far side of an ocean. As dark energy accelerates the expansion of space itself, the ocean between us is widening at an ever-increasing rate. One by one, those distant cities will slip beyond our cosmic horizon. This isn't because they are moving away through space faster than light, but because the space between us is expanding so rapidly that their light can no longer cross the ever-widening gulf to reach us. The consequences of this are staggering to contemplate. In tens of billions of years, an astronomer in our local group would look out into a sky that is almost entirely black. All the galaxies we see today, all the evidence of a vast and structured cosmos, will have been redshifted into oblivion. Their light will have been stretched to wavelengths so long, so feeble, that it is undetectable. The universe will appear, for all intents and purposes, to contain only our own merged Milky Way Andromeda galaxy, adrift in an infinite, empty void. The evidence for the Big Bang, the expanding universe, the cosmic microwave background, all of it will be lost to future civilizations, forever beyond their observational reach. Their universe will be a static, island universe, with no clues to suggest it was ever any different, and the end of light is only the beginning. As the eons stretch on, even the local universe will face a grim fate. Star formation will eventually consume all the available gas, and the last stars will flicker out, leaving behind a cosmic graveyard of black holes, neutron stars, and cold, dead stellar cinders. Over unimaginable timescales, even these remnants may evaporate due to quantum processes. The universe will approach a state of absolute equilibrium, a uniform temperature just a fraction of a degree above absolute zero. There will be no energy gradients, no hot spots or cold spots, no structure of any kind. It will be a state of maximum entropy where no work can be done and no complex process can occur. It is the ultimate thermodynamic silence, a final, frozen state where time itself becomes meaningless. This is the future dictated by a constant dark energy, a repulsive force that seems to be an intrinsic property of the vacuum of space itself, a force that is, in a way, the very antithesis of life and complexity. To understand dark energy, then, is not just an academic exercise. It is to stare into the abyss and ask the most fundamental question about our existence. Is this truly the end of everything, or could the dark energy that governs our fate be capable of change? Measuring the properties of dark energy is like trying to study the wind by watching its effect on distant clouds. You cannot see the force itself, only the profound changes it leaves in its wake. To do this, astronomers have become cosmic surveyors, wielding some of the most ingenious tools ever developed to chart the invisible. The original and most dramatic of these tools is the Type Ia supernova, a stellar explosion of such consistent brilliance that it acts as a standard candle across the vast gulfs of intergalactic space. The principle is beautifully straightforward. If you know the true, intrinsic brightness of a light source, you can calculate its distance by how dim it appears from your vantage point. A car's headlights appear dazzling up close but fade to a faint glimmer miles away. The degree of dimming directly tells you the distance. A Type Ia supernova shines with a known, predictable luminosity because each one is a cosmic copycat. They all occur in a binary star system where a white dwarf star steals material from its companion until it reaches a critical mass limit, triggering a thermonuclear detonation of such violence that, for a few glorious weeks, it can outshine an entire galaxy. Because this tipping point is always the same, the peak brightness is always the same, making these events perfect cosmic mile markers. By meticulously observing these distant stellar beacons, astronomers perform a kind of cosmic archaeology. They measure two things: the supernova's apparent brightness, which reveals its distance, and its redshift, how much the expanding universe has stretched its light toward the red end of the spectrum. By comparing supernovae from different eras, they can reconstruct the expansion history of the universe. The shocking discovery in the late 1990s was that the most distant supernova, those whose light has been traveling for billions of years, were fainter than expected. This meant they were farther away than they should have been in a universe whose expansion was slowing down. The only possible explanation was that the expansion had been slower in the past and has since accelerated, pushing these supernovae to greater distances. It was as if you marked the position of a boat drifting on a river, only to return later and find it was much farther downstream because the current had inexplicably started flowing faster. These dying stars, observed at the peak of their brilliance, delivered the undeniable message that a mysterious repulsive force was taking control of the cosmos. While supernovae provide the brilliant, individual flashes that first revealed the acceleration, a second, more subtle technique maps the universe's structure on the very largest scales, using frozen echoes from the dawn of time. This method relies on Baryonic acoustic oscillations, or BAO. To understand BAO, we need to travel back to the universe's first few 100,000 years, when it was a searing, opaque plasma of light and matter. In this dense, hot soup, gravity tried to pull matter together into clumps, while the intense pressure of the trapped radiation pushed it outward. This push and pull created colossal sound waves, spherical pressure waves, that rippled through the primordial plasma, much like the sound waves from a stone dropped in a pond. These waves traveled outward at nearly half the speed of light until a pivotal moment. The universe cooled enough for atoms to form, allowing light to decouple from matter and travel freely. At that instant, about 380,000 years after the Big Bang, the waves froze in place, their progress halted as the universe became transparent. The result is a fascinating cosmic fossil. These frozen waves left a distinct imprint on the distribution of matter, just as the ripples from that stone would leave a ring of floating leaves on the pond's surface. The Baryonic acoustic oscillations left a subtle, preferred scale in the universe. Galaxies today have a slight statistical tendency to be separated by a specific distance, about 500 million light-years, which is the radius of those primordial sound waves at the moment they were frozen. This scale acts as a standard ruler etched across the entire cosmos. By conducting enormous galaxy surveys, like the Dark Energy Survey or the ambitious Future Legacy Survey of Space and Time from the Vera Sea. Rubin Observatory, astronomers can measure this standard ruler at different cosmic epochs. They map the three-dimensional positions of millions of galaxies, and within that vast cosmic cartography, they look for this characteristic separation. By measuring how the apparent size of this ruler changes over time, they can trace the expansion history of the universe with extraordinary precision. If the universe expands faster, the ruler at a greater distance will appear more compressed in our measurements. It's a geometric test independent of the brightness of any single object, providing a powerful cross-check on the supernova results and confirming the accelerating expansion with a completely different set of physics. Together, these two methods, the brilliant flashes of dying stars and the subtle statistical clustering of galaxies, form a powerful partnership in the quest to understand dark energy. They allow scientists to constrain its equation of state, a key parameter that describes the relationship between its pressure and density. If dark energy is indeed a simple cosmological constant, as Einstein proposed, this parameter should equal exactly -1. However, if it is something more dynamic and exotic, like a quintessence field that evolves over time, this value could be different. The supernova data provides a direct measure of how distances have changed, while the BAO data provides a robust measurement of how the geometry of the universe has evolved. By combining them, cosmologists can tightly constrain this crucial number, testing the very nature of the force that dominates our universe. Every new supernova observed and every new galaxy mapped in these vast surveys is like taking the pulse of the cosmos, a precise measurement of its accelerating heartbeat, and with each beat, we learn a little more about the mysterious rhythm that will dictate the ultimate fate of all we see. If you think the discovery of dark energy was a shock, then prepare yourself for a puzzle so profound and so bizarre that it has been called the worst prediction in the entire history of physics. We've just seen how Einstein's cosmological constant was resurrected to explain the accelerating universe, representing a constant energy density inherent to the vacuum of space itself. But this elegant solution comes with a catastrophic price tag, one that reveals a terrifying rift at the very heart of our understanding of reality. This is the cosmological constant problem, and it's not just a small error or a minor miscalculation. It is a discrepancy of such staggering magnitude that it defies all common sense, a number so wrong it threatens to undermine the very foundations of modern physics. To grasp the sheer scale of this problem, we need to understand what our two most successful theories are telling us. On one hand, we have our theory of the very large Einstein's general relativity, which describes the smooth, geometric fabric of spacetime and the cosmos. Observations of dark energy tell us that the vacuum energy density must be incredibly small, a tiny, whisper-thin value that allows galaxies to form and the universe to evolve as it has. This is the observed reality. On the other hand, we have our theory of the very small quantum field theory, which describes a wild, chaotic subatomic world where particles flicker in and out of existence. When physicists use this theory to calculate the energy of the vacuum, they don't get a small number. They get a number that is explosively, unimaginably large. The quantum vacuum is not an empty void. It is a seething, bubbling foam, a tumultuous sea of virtual particle-antiparticle pairs constantly popping into existence and annihilating each other. Every cubic centimeter of empty space, according to quantum mechanics, should be boiling with this latent energy. Now, let's put a number on this insanity. The value of the vacuum energy density inferred from the accelerating expansion of the universe is about 10 to the power of -8 ergs per cubic centimeter. It is a minuscule sliver of energy. The value predicted by summing up all the contributions from these quantum fluctuations is about 10 to the power of 112 ergs per cubic centimeter. The difference between these two numbers is a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To say this is a colossal mismatch is the understatement of the millennium. It would be like using the most sophisticated theories of physics to predict the mass of an elephant, and your calculation giving you an answer that is heavier than the entire observable universe. The error is so vast, so complete that it cannot be ignored. It is a screaming alarm bell telling us that something is fundamentally broken in our description of nature. This isn't just a mathematical inconvenience, it's a direct confrontation between our two most powerful theories. General relativity and quantum mechanics have never gotten along. One describes the force of gravity as the smooth curvature of space-time, while the other describes particles as probabilistic waves and fields. The cosmological constant problem is the most dramatic and embarrassing manifestation of this divorce. It shows that when we try to plug the quantum energy of the vacuum into Einstein's equations for gravity, the result is a catastrophic failure. The universe, according to this naive combination, should have torn itself apart moments after the Big Bang or collapsed into a singularity instantly. The fact that we exist in a stable, slowly accelerating universe with a vacuum energy that is almost, but not quite, zero is a mystery that keeps physicists awake at night. So, where do we go from here? How do we solve a problem of this magnitude? Scientists have proposed several daring, and in some cases deeply philosophical, escape routes. One possibility is that we are simply wrong about the quantum vacuum. Perhaps there is a hidden symmetry or a cancellation mechanism we haven't discovered yet, where the positive and negative contributions from different particles and fields perfectly balance out to produce a net value of nearly zero. This would be an elegant solution, but so far, no such perfect cancellation has been found in our current theories. Another, more radical idea is that our theory of gravity is incomplete. Maybe Einstein's general relativity needs to be modified not just on galactic scales, but on the scale of the entire universe, in a way that naturally explains the tiny value we observe for dark energy. Then there is the most controversial and mind-bending proposal of all, the anthropic principle within the framework of the multiverse. This line of reasoning suggests that perhaps the cosmological constant isn't determined by a fundamental law, but is instead a random variable that can take on different values in different, disconnected regions of a much larger multiverse. In the overwhelming majority of these universes, the value of the cosmological constant is enormous, and those universes either expand too rapidly for any structure to form or recollapse too quickly. We, of course, find ourselves in one of the incredibly rare universes where the value is just right, small enough to allow galaxies, stars, planets, and ultimately, life to evolve. In this view, the value of dark energy isn't dictated by a beautiful equation. It is an environmental accident, a cosmic lottery ticket that we just happen to win. While this idea offers a potential explanation, it is deeply unsettling to many physicists because it moves cosmology from a predictive science to a post-dictive one. It explains why we observe this specific value because we are here to observe it, but it doesn't predict it from first principles. The cosmological constant problem is therefore much more than a technical puzzle. It is a glaring signpost, a beacon pointing toward the next great revolution in physics. It tells us in no uncertain terms that our current understanding is provisional. We are missing a crucial piece, a theory that can seamlessly weave together the quantum world with the gravitational cosmos, a theory of quantum gravity. Whether the solution comes from string theory, loop quantum gravity, or a completely new idea yet to be conceived, resolving this 120 orders of magnitude error is the key that will unlock a deeper understanding of reality. It stands as a monument to our ignorance, a humbling reminder that for all our knowledge, the universe still holds profound secrets that challenge the very core of our scientific worldview. But what if the very nature of this dark energy isn't fixed? What if the force driving the cosmos apart isn't a steady, unchanging constant, but something that ebbs and flows, a dynamic presence that has a history and a future all its own? This captivating possibility takes us beyond Einstein's cosmological constant into a more exotic and dramatic theoretical realm known as quintessence. The name itself, derived from the ancient Greek concept of a fifth element beyond earth, air, fire, and water, hints at its revolutionary nature. Imagine the cosmological constant as a feature permanently etched into the fabric of space-time, like a fundamental setting on a cosmic control panel that never changes. Quintessence, by contrast, is more like a cosmic weather system, a field that permeates all of space but whose energy density can slowly shift and evolve over billions of years. It's the difference between a rock-solid foundation and a vast, slow-moving ocean whose tides can subtly alter the universe's expansion rate across cosmic epochs. This idea opens up a far wider and more speculative range of possible futures for our universe. If dark energy is a true cosmological constant, then the acceleration we see today will continue at a steady pace, leading to the long, cold, and lonely big freeze we described earlier. But if quintessence is real, the outcome could be far more violent and final. Theorists have explored models where the repulsive force of quintessence doesn't just remain constant, but actually grows stronger over time. In this most extreme scenario, the accelerating expansion wouldn't just push galaxies apart. It would eventually overcome every force that holds structures together. First, the gravitational bonds tethering galaxy clusters to one another would be severed. Then, the immense gravity holding individual galaxies like our Milky Way intact would be overwhelmed, and the galaxy would be torn asunder, its stars scattered into the void. The violence wouldn't stop there. The expansion force would then grow so powerful that it would rip apart solar systems, pulling planets from their stars. In the final, terrifying moments, it would overcome the electromagnetic forces holding atoms together, and then the strong nuclear force binding atomic nuclei. This apocalyptic end is known as the Big Rip, a catastrophic dissolution of all matter and space-time itself, a final, instantaneous erasure of structure at every scale. While this is a speculative and extreme possibility, it illustrates a profound point. If dark energy is dynamic, then the ultimate fate of the cosmos is not yet written in stone. The key to unlocking this mystery lies in a single, crucial parameter that cosmologists call the equation of state, denoted by the letter W. This number describes the relationship between the pressure and density of dark energy. For a simple cosmological constant, this value is fixed at exactly -1. It's a clean, simple, and static number. For quintessence, however, this value can be different from -1, and more importantly, it can change over the history of the universe. Detecting even the tiniest deviation from -1 would be a monumental discovery, shattering the simple cosmological constant model and forcing a radical rethink of dark energy. This is the grand challenge that now drives the field of observational cosmology. It's a hunt for an incredibly subtle signal, like trying to measure whether the pitch of a constant, universal hum has shifted by an infinitesimally small amount over billions of years. To make this measurement, scientists are deploying all the tools at their disposal in a coordinated, global campaign. They use Type Ia supernova as cosmic mile markers, just as they did for the initial discovery, but now with a much finer-toothed comb, seeking to trace the expansion history with unprecedented precision to see if the acceleration has ever wavered. They analyzed the Baryonic acoustic oscillations, that fossilized imprint of primordial sound waves in the galaxy distribution, to act as a cosmic standard ruler, measuring the geometry of the universe across different epochs. They even used the most distant light sources of all, quasars, to map the distribution of intergalactic hydrogen gas, which also holds clues to the expansion rate over cosmic time. By combining all these methods, astronomers are essentially trying to create a high-resolution movie of the universe's expansion, frame by frame, looking for any telltale sign that the push of dark energy was stronger or weaker in the past than it is today. The next generation of astronomical observatories is being designed with this very question as their primary mission. The Vera C. Rubin Observatory's legacy survey of space and time will catalog billions of galaxies, providing a colossal dataset for both supernova and BO studies. The Euclid Space Telescope and the Nancy Grace Roman Space Telescope are specifically engineered to measure the shapes and positions of galaxies with exquisite accuracy, using weak gravitational lensing and galaxy clustering to probe the nature of dark energy with a precision we can only dream of today. These instruments represent humanity's best hope for answering this fundamental question. Is the dark energy that governs our fate a simple, eternal constant, a static feature of the vacuum? Or is it a dynamic field, a quintessence that has its own story to tell, a story that could lead to a future of unimaginable violence or perhaps something even stranger that we have not yet conceived? The answer will not only tell us how the universe will end, but it will reveal something profound about the fundamental laws of physics that have been in play since the very first moments of time. Picture the entire cosmic timeline as a great and epic battle, a slow-motion tug-of-war between two invisible giants. In one corner stands dark matter, the universe's great architect, its immense gravitational pull a relentless, gathering force that works to draw the cosmos together. In the other corner is dark energy, a mysterious and pervasive pressure woven into the very fabric of space, a repulsive force that actively pushes the universe apart. For billions of years, this struggle defined the fate of everything, a delicate balance between construction and dispersal that has dictated the story of our universe from its first moments to the distant future we now foresee. This isn't a conflict of explosions and fire, but a silent, slow, and profound contest between the two fundamental influences that make up 95% of all reality. In the universe's fiery youth, dark matter was the undisputed champion. From the first moments after the Big Bang, as the cosmos expanded and cooled, dark matter's unique property of being immune to the intense radiation pressure gave it a critical head start. It began to collapse under its own gravity immediately, forming a vast, invisible network of filaments and halos, the cosmic web's foundational scaffolding. As this gravitational landscape took shape, it provided the wells and valleys into which normal, baryonic matter could later flow. Think of dark matter as the diligent construction crew that arrives first at a building site, laying the foundation and erecting the steel framework before any bricks are ever laid. During this era, the universe was dense, and the gravitational pull from all this matter, both dark and visible, was overwhelming. The expansion that began with the Big Bang was still proceeding, but it was steadily slowing down like a car coasting up a long, gradual hill, its speed decreasing with every passing moment under the relentless pull of gravity's brakes. It was within this slowing, gathering cosmos that the first galaxies swirled to life, that stars ignited, and that the grand structures we admire today were given the time and the gravitational focus to assemble themselves. Without dark matter's dominant grip during these formative eons, the universe would have expanded too rapidly, its matter too diluted for such magnificent structures to ever coalesce. But as the eons passed, a fundamental shift was occurring, driven by the simple, relentless fact of cosmic expansion. Imagine a vast crowd of people scattered in a giant plaza. At first, they are packed tightly together, and their mutual attraction makes it easy for them to form small groups and clusters. This was the early, matter-dominated universe. But as the plaza itself begins to stretch, expanding in all directions, the people become more and more spread out. Their density decreases. The force of their collective attraction weakens as the distance between them grows. This is exactly what happened to dark matter and normal matter. Their gravitational influence, which depends on density, began to wane as the universe became a more spacious, more dilute place. Meanwhile, the other great force in our cosmic drama, dark energy, was playing by a completely different set of rules. If dark energy is indeed a cosmological constant, an energy inherent to the vacuum of space itself, then its density does not dilute. In every new cubic centimeter of space that is created as the universe expands, the same amount of this repulsive energy appears. So while matter's gravitational pull was fading, dark energy's push remained constant, and thus its relative influence grew stronger with every passing billion years. This led to one of the most pivotal turning points in the entire 14 billion-year history of the cosmos, the moment of transition. Roughly 5 billion years ago, the balance of power officially shifted. The universe had expanded to the point where the now diluted gravitational pull of matter could no longer compete with the steady, unyielding pressure of dark energy. The great tug-of-war rope, which had been slowly moving in dark matter's favor, suddenly began to slide the other way. The cosmic expansion, which had been steadily slowing since the beginning, reached a point of minimum velocity and then, defying all earlier expectations, began to accelerate. It was as if our car, which had been slowing as it climbed the hill, suddenly crested the summit and found itself on a downward slope with its own accelerator pedal pressed to the floor. This was the moment the universe switched from deceleration to acceleration, a fundamental change in its very mode of existence. The era of structure building, dominated by dark matter's attractive gravity, was gradually giving way to an era of dispersal, governed by dark energy's repulsive force. The timing of this transition is not a minor detail. It is a crucial clue that cosmologists are desperate to understand with ever greater precision. Why 5 billion years ago? Why not sooner or later? The answer to this question is deeply encoded in the relative strengths and fundamental natures of dark matter and dark energy. The fact that the switch happened after galaxies and clusters had already formed is, from our perspective, incredibly fortunate. It allowed the universe the necessary time to build the complex structures that would eventually give rise to stars, planets, and us. If dark energy had become dominant too early, say just a billion years after the Big Bang, its repulsive force would have prevented matter from ever clumping together. Galaxies would never have formed, and the universe would be a dark, empty, and featureless void. The precise moment of this cosmic handover therefore feels strangely fine-tuned, a detail that has profound implications for our understanding of physics and our own place in the cosmos. By measuring the expansion history with extreme accuracy, using supernova and baryon acoustic oscillations, scientists are essentially trying to replay the tape of this cosmic transition, to understand the exact conditions that allowed our rich and structured universe to emerge before the Great Dispersal began. This ongoing tug-of-war continues to shape our cosmic environment today. We live in a peculiar and fascinating moment, a kind of cosmic twilight. The grand architecture built by dark matter is still firmly in place. Our Milky Way galaxy remains gravitationally bound, as does our local group of galaxies. On these scales, dark matter's gravity still reigns supreme. but look beyond our local neighborhood to the vast distances between galaxy clusters, and you see the clear and dominant hand of dark energy at work, pushing these great islands of matter apart at an ever-increasing rate. We are situated in a time where we can still look out and see the glorious, structured universe that dark matter built, while simultaneously gathering the evidence for the accelerating future that dark energy promises. This balance, this temporary and precious equilibrium between two invisible titans, has given us a window to observe, to comprehend, and to wonder at the cosmic forces that have crafted our past and will ultimately dictate our long-term future. The universe we see today, with its brilliant galaxies set against a dark, expanding backdrop, is a direct snapshot of this ongoing confrontation, a single frame in a cosmic film whose final scene is still being written by the silent struggle between the pull of darkness and the push of the void. But how do we possibly test these grand theories about the dark universe? We can't put a galaxy in a laboratory beaker, and we certainly can't rewind the cosmos to run the experiment again. This is where the power of modern supercomputing transforms from a technological marvel into an essential tool for cosmic discovery. By writing the laws of physics into immense lines of code, cosmologists have constructed entire virtual universes inside machines, digital laboratories where they can watch the saga of dark matter and dark energy play out from the Big Bang to the present day. These aren't simple video game recreations. They are some of the most complex simulations ever attempted by humanity, involving billions of particles and equations that would take centuries to solve by hand. Projects with evocative names like Illustris TNG and Eagle begin their digital life with the same initial conditions we observe in the cosmic microwave background, that faint, fossilized light from the infant cosmos. They program in the standard recipe of the lambda CDM model, a universe made of dark energy, cold dark matter, and a small sprinkling of ordinary atoms. Then, with a virtual press of a button, they set the simulation in motion, applying the relentless force of gravity to countless dark matter particles, and watching as they begin their cosmic dance over billions of simulated years. What unfolds is nothing short of magical. From a nearly smooth, uniform beginning, the dark matter, responding only to gravity, begins to clump and collapse. A vast, intricate cosmic web emerges spontaneously, with shimmering filaments connecting dense, dark matter halos, all while the background expansion of space, driven by dark energy, steadily stretches the entire virtual cosmos. But the simulation doesn't stop with the darkness. The most advanced models incorporate sophisticated physics for the normal matter that gets swept along for the ride. As gas falls into the gravitational wells of the dark matter halos, the code calculates its cooling, its collapse, and the eventual ignition of the first stars. It models the ferocious feedback from supernova explosions that blast gas back out into the void, and the immense gravity of growing supermassive black holes at galactic centers, whose active jets can heat surrounding gas and shut down star formation. This intricate interplay between the dark universe's gravitational blueprint and the complex, messy astrophysics of ordinary matter is what allows these virtual worlds to birth galaxies that look astonishingly like our own. We can watch a majestic spiral galaxy form, complete with a central bulge and graceful arms, not because an artist designed it, but because it emerged naturally from the fundamental laws programmed into the simulation. The true power of these digital universes is revealed when we hold them up against the real one. After running a simulation that may take months on a supercomputer, cosmologists compare its final state to massive sky surveys like the Sloan Digital Sky Survey. They look at the statistical properties, the distribution of galaxy sizes, their shapes, how they cluster together in groups and chains, and the overall architecture of the cosmic web. The fact that simulations like Illustris TNG and Eagle can reproduce the large-scale structure of our observable universe with such breathtaking fidelity is one of the strongest pillars supporting the entire Lambda CDM model. It's a powerful consistency check. If our theory of dark matter and dark energy were fundamentally wrong, it's incredibly unlikely that these simulations, built upon that very theory, would so successfully replicate the intricate tapestry of the cosmos we see through our telescopes. This success gives us tremendous confidence that we are on the right track, that the dark side of the universe, while invisible, operates according to rules we are beginning to comprehend. Yet, these simulations are far more than just validators of established theory. They are also powerful discovery tools that highlight where our understanding falls short. This is where the small-scale problems we discussed earlier come sharply into focus. When researchers zoom in on individual dwarf galaxies within the simulation, they might find that the distribution of dark matter in their centers is too peaked, the cusp problem compared to real-world observations. Or they might count the number of small satellite galaxies swirling around a simulated Milky Way and find far more than we actually see, the missing satellites problem. These aren't failures, they are golden opportunities. These discrepancies are like error messages from the universe, pointing directly to physics that we have either modeled incorrectly or have not yet included in the code. Perhaps dark matter isn't perfectly cold and collisionless, but has some slight interaction. Maybe the feedback from supernova is even more powerful than we thought, capable of reshaping the inner regions of dark matter halos. The simulation acts as a crucible, forcing us to refine our ideas and propose new physics that can bridge the gap between the virtual and the real. In this way, supercomputer simulations are not just passive models. They are active guides, directing the gaze of our most powerful telescopes towards the most promising and puzzling corners of the sky, telling us exactly what to look for next. This grand quest to solve the mysteries of dark matter and dark energy is not just a theoretical exercise. It is fueling a new golden age of astronomical engineering, driving the creation of revolutionary observatories that will act as our collective eyes, piercing the veil of darkness with a clarity we have only dreamed of. We are on the cusp of a data revolution, a coordinated global assault on the unknown that will see our maps of the cosmos transformed from rough sketches into exquisitely detailed blueprints of the invisible. This is not the work of a single telescope, but a symphony of instruments, each playing a unique part in the orchestra of discovery, both on the ground and in the pristine darkness of space. Leading this charge from a mountaintop in Chile is the Vera Rubin Observatory, a facility built around one of the largest digital cameras ever constructed. Its mission is the Legacy Survey of Space and Time, or LSST, a project of almost unimaginable scope. For 10 years, this observatory will repeatedly photograph the entire southern sky, not just once, but over and over, creating a colossal, dynamic movie of the cosmos. It will detect billions of galaxies and track the subtle changes in their light, but its true power lies in its ability to perform weak gravitational lensing on an industrial scale. By analyzing the tiny, coherent distortions in the shapes of countless distant galaxies, the LSST will effectively trace the gravitational field of the intervening dark matter. It will produce a three-dimensional mass map of the universe, the most detailed census of the cosmic skeleton ever made, revealing the hidden architecture of the cosmic web in stunning detail, and showing us exactly how dark matter is distributed across space and time. Soaring above the distorting effects of Earth's atmosphere, the European Space Agency's Euclid Space Telescope is a dedicated dark universe detective. Launched into the silence of space, Euclid's mission is to measure the geometry of the cosmos with breathtaking precision. It, too, will use weak gravitational lensing, but with the added stability and clarity that only a space-based platform can provide. Simultaneously, it will create the largest ever map of galaxy clustering, charting the positions of billions of galaxies. By combining these two powerful techniques, Euclid will trace the influence of both dark matter through its lensing effects and dark energy through its impact on how the clustering of galaxies has evolved over the last 10 billion years. It is specifically engineered to test whether dark energy is truly a cosmological constant or something more dynamic, like quintessence, by measuring the universe's expansion history with a finer-toothed comb than ever before. Joining this cosmic cartography effort is NASA's and Nancy Grace Roman Space Telescope, a powerhouse instrument named for the pioneering astronomer often called the Mother of Hubble. The Roman Space Telescope shares a similar ambition to survey vast swaths of the sky, but it brings its own unique set of tools to the problem. With a field of view 100 times larger than the Hubble Space Telescopes, it will conduct high-precision surveys at infrared wavelengths, peering through cosmic dust to see the large-scale structure of the universe with exceptional clarity. Its surveys will provide another, independent and incredibly precise measurement of the Baryonic acoustic oscillations, that fossilized ruler from the early universe. By comparing this standard ruler at different cosmic epochs, scientists using Roman's data will be able to chart the expansion history of the universe with minimal systematic errors, putting the properties of dark energy to the most rigorous test yet. While these optical and infrared telescopes scan the skies, a completely different kind of observatory is taking shape on the ground, one that will listen to the universe rather than just look at it. The Square Kilometre Array, or SCAR, is not a single dish but a vast network of thousands of radio antennas spread across South Africa and Australia. When fully operational, it will form the most sensitive radio telescope in history, with a total collecting area of, as the name suggests, approximately 1 square kilometre. The SKA's strategy for probing the dark universe is brilliant and indirect. It will map the distribution of neutral hydrogen gas, the most abundant element in the cosmos, across billions of light years. By measuring the faint 21-centimeter radio emission from this hydrogen, the SKA can effectively see where galaxies are forming and track how the vast voids and filaments of the cosmic web evolve. It will create a three-dimensional map of the universe's structure that stretches back to its first billion years, providing a crucial independent check on the results from optical telescopes and offering a unique window into how dark energy influenced the growth of structure during the universe's adolescent years. Together, these monumental facilities represent a unified, global endeavor, a testament to humanity's insatiable curiosity. The Vera C, Rubin Observatory, the Euclid and Roman Space Telescopes, and the Square Kilometre Array are not competitors. They are collaborators in a grand experiment. They will cross-check each other's findings, combat systematic errors, and provide a multi-wavelength, multi-technique view of the dark cosmos that is far greater than the sum of its parts. The next decade promises not just a trickle of new data, but a veritable flood, a deluge of information that will contain within it the clues we need to finally understand the true nature of dark matter and the destiny dictated by dark energy. We are building the tools that will, we hope, finally allow us to read the hidden script of the cosmos, written in the language of gravity, geometry, and the profound darkness that binds it all together. This revelation pushes us far beyond the boundaries of astrophysics and into the realm of profound philosophical inquiry. For centuries, our entire understanding of existence was built upon a fundamental, yet unexamined, assumption that the universe is essentially what we can see and touch. We looked up at the stars and believed we were witnessing the cosmos in its entirety. But the discovery that 95% of reality is composed of dark matter and dark energy shatters that assumption completely. We are like deep-sea creatures who have spent our entire lives at the bottom of the ocean, constructing a model of the world based solely on the pressure, the dim light, and the creatures that live in our abyssal plane. We never knew about the concept of an atmosphere, the burning sun, the vast continents, or the billions of other life forms thriving in a medium we couldn't even conceive of air. Our reality was defined by water, and we assumed that was all there was. Similarly, we have been living in a universe defined by light and matter, completely unaware that we are swimming in an ocean of darkness, that the very space we consider empty is teeming with a dominant, repulsive energy, and that the true architects of the cosmos are completely invisible to us. This forces a radical humility upon us. The Copernican revolution first dethroned us from the physical center of the universe. Now, the dark universe revolution dethrones us from the center of reality itself. It challenges the deeply ingrained anthropocentric view that the cosmos is somehow designed for our perception or our understanding. The universe is not obligated to be intuitive to the human brain, which evolved to solve problems of survival on the African savanna, not to intuitively grasp the nature of cosmic nothingness or invisible matter. The rules governing 95% of existence operate in a domain utterly foreign to our daily experience. We are like ants crawling across a fresco by Michelangelo. We can perceive the texture of the paint and the cracks in the plaster, but we have no capacity to comprehend the grand artistry, the story being told, or the artist's intent. We are limited observers, decoding a masterpiece with senses that are only equipped to notice the tiniest, most superficial details. This leads to an unsettling but liberating conclusion. Our perception of reality is not just limited, it is a carefully constructed illusion. The world of planets, stars, and galaxies, the entire breathtaking pageant of the night sky, is merely the surface glitter, the decorative frosting on a cake whose substance we cannot taste. The true substance of the cosmos, the dark matter and dark energy, is the cake itself. This suggests that what we call reality is provisional and incomplete. Our scientific models are incredibly successful at describing the 5% we can see, but they are, by definition, a description of the exception, not the rule. It forces us to question what other fundamental aspects of existence we might be missing. Are there other layers of reality, other forces or substances that are even more dominant or strange, making dark matter seem as familiar as a stone by comparison? The dark universe is a humbling reminder that we are at the very beginning of a long journey of discovery, and that our current understanding, for all its sophistication, is likely a crude sketch of a far more magnificent and complex truth. We are not the central players in the cosmic story. We are fleeting spectators in a vast dark drama whose main actors remain hidden behind an impenetrable curtain. This staggering mismatch, this one followed by 120 zeros, is not just a problem, it's a crisis. It screams that our understanding of fundamental physics is broken, forcing scientists to consider explanations that were once confined to the realm of philosophy and science fiction. One of the most radical, and for some, most unsettling proposals to escape this dead end is to invoke the concept of the multiverse, and with it, the controversial anthropic principle. The logic here takes a dramatic turn away from traditional scientific reasoning. Instead of asking, what fundamental law dictates the tiny value of dark energy, this approach asks a different question entirely. Could it be that we are simply asking the question in the only kind of universe where the question can be asked? Imagine a cosmic lottery, a reality generator churning out new universes with every fleeting moment. In this vast, perhaps infinite, multiverse, the fundamental constants of nature are not universal laws but random variables, set to different values in each newly born cosmic bubble. In the overwhelming majority of these universes, the roll of the dice for the cosmological constant comes up wrong. In many, the value of dark energy is colossal, so immense that the universe expands with such ferocious speed in its first instance that space-time rips itself apart before a single atom can ever form. In others, the value might be a large negative number, causing the cosmos to collapse back in on itself in a catastrophic Big Crunch almost immediately after it begins. Structure, complexity, and life are impossible in these places. They are stillborn universes, empty and barren. But in an incredibly rare subset of this cosmic ensemble, by sheer random chance, the dark energy value falls within a narrow, habitable window. It is small enough to allow gravity to work its slow, patient magic over billions of years, pulling matter into galaxies, stars, and planets, yet not exactly zero, allowing for the eventual accelerated expansion we observe. We, of course, find ourselves living in one of these exceptionally rare, bio-friendly universes. Our existence as observers is not a coincidence, it is a selection effect. We are here because this universe, against all odds, has the right conditions for us to be here. This is the core of the anthropic principle. This line of reasoning offers a breathtaking, if deeply humbling, solution to the fine-tuning problem. The value of dark energy isn't dictated by a beautiful, elegant equation we haven't yet discovered. It is a cosmic accident, a random environmental condition of our particular cosmic neighborhood. The reason we measure such an inexplicably small number is that in the universes where it is any larger, there is no one around to measure anything at all. This idea connects the very largest scales of cosmology, the fate of the entire universe, with the most intimate conditions necessary for our own existence. It suggests that the properties of the cosmos and the emergence of conscious life are inextricably linked, not by design but by a simple statistical filter. However, this proposal is deeply controversial and philosophically troubling to many scientists. The primary criticism is that it seems to move the goalposts of science. Traditionally, physics aims to be predictive. A good theory makes specific, testable forecasts about what we should observe. The anthropic explanation, its detractors argue, is post-dictive. It doesn't predict the value of dark energy. It merely uses our existence to explain why we observe the value we do after the fact. It can account for almost any outcome, making it seem, to some, like an untestable, almost theological argument that could potentially halt the search for a deeper, more fundamental physical law. If we accept that constants are just random, then what is left for fundamental physicists to actually explain? Yet, proponents counter that the multiverse is not necessarily untestable. If our universe is just one bubble in a frothing multiverse, it's possible that other bubbles could, in principle, leave an imprint on our own. Some theories suggest that collisions between these budding universes could create detectable signatures in the cosmic microwave background, strange asymmetries or patterns in the fossilized light of the Big Bang. While no such evidence has been found, the possibility remains that the multiverse could one day move from metaphysics into the realm of observational science. Furthermore, this perspective forces a profound shift in what we consider a fundamental law. Perhaps the true fundamental law is not the specific value of the cosmological constant. but the mechanism that generates the multiverse and allows for the variation of constants in the first place, such as the eternal inflation of string theory's landscape. The challenge, then, is not to explain one number, but to explain the process that produces all possible numbers. This debate places us at a fascinating frontier where the concrete world of mathematical physics directly confronts the abstract realms of philosophy and probability. It forces us to grapple with the very meaning of a scientific explanation and our place in the cosmos. Are we the temporary inhabitants of a universe with uniquely tailored laws, or are we simply incredibly lucky winners of a cosmic lottery that has produced untold numbers of losing tickets? The anthropic principle, for all its controversies, provides a stark and powerful reminder that our observations of the universe are not independent of the conditions required for us to exist. In the search for the origin of dark energy, we may ultimately be forced to confront the possibility that the answer is written not in the equations of physics alone, but in the simple, statistical necessity of our own presence as witnesses to the cosmic dark. To truly appreciate the monumental role dark matter played in the cosmos, we need to travel back to a time before time itself had any real structure to mark its passage, to the universe's first few 100,000 years. This was not an era of stars and galaxies, but a searing, chaotic fireball, a dense and opaque plasma where the basic ingredients of reality were locked in a constant, violent struggle. In this primordial inferno, normal matter, the protons and electrons that would one day make up everything we can see, was not free. It was shackled to light itself. Every particle of normal matter was constantly battered by an intense, relentless sea of radiation, a pressure so overwhelming that gravity, the great architect of structure, stood no chance. Any slight, tentative clump of matter that tried to form under its own weak gravitational pull would be instantly blown apart by the sheer force of the photons pushing against it. It was a cosmic stalemate, a universe where the forces of construction and dispersal were perfectly, frustratingly balanced, trapping the ordinary stuff of creation in a hot, featureless fog. This is where dark matter's unique and silent nature gave it the ultimate cosmic advantage. While normal matter was trapped in its radiant prison, dark matter was the ghost at the feast. Completely indifferent to the electromagnetic force, it felt no radiation pressure whatsoever. The blinding light that controlled the normal universe streamed right through it as if it weren't even there. This meant that from the very first moments, dark matter was free to listen to the one force it could feel, gravity. And so, while the ordinary universe remained a smooth, hot soup, the dark universe began to stir. The tiniest quantum fluctuations from the Big Bang, microscopic ripples in the fabric of space-time, were all the invitation it needed. These minuscule overdensities, regions where dark matter was ever so slightly more concentrated, began to act as gravitational anchors. Their slightly stronger pull started to attract nearby dark matter, slowly, patiently gathering more and more of the invisible substance into growing clumps. In the absolute darkness, away from the blinding light of the plasma, the cosmic skeleton began to form, laying down the first, faint blueprints for everything that was to come. This patient, invisible work continued for hundreds of thousands of years, a silent construction project happening in a dimension inaccessible to light. The dark matter condensed into a vast, intricate network of filaments and halos, a gravitational landscape of hills and valleys being sculpted across the expanding cosmos. Then a pivotal event occurred, one that cosmologists call recombination. The universe had expanded and cooled enough for the electrons and protons, which had been bouncing around freely, to finally combine and form stable, neutral hydrogen atoms. In that moment, the universe underwent a profound transformation. it became transparent. The light that had been trapped for so long was suddenly set free, releasing the flash we now observe as the cosmic microwave background. For the normal matter, this was emancipation. No longer bullied by radiation, it was finally free to move under the influence of gravity alone. And where did gravity direct it to go? Straight into the waiting gravitational wells that the dark matter had been preparing for millennia. Think of it as a cosmic rainfall. The dark matter had spent ages carving out riverbeds and lakes across the expanding landscape of space. Now, for the first time, the normal matter in the form of hydrogen and helium gas was free to flow. It cascaded along the invisible filaments of the dark matter web, pooling in the deepest gravitational valleys, the dark matter halos. This was the decisive handoff, the moment when the invisible architect passed the blueprint to the visible construction crew. The gas, now gathered in these dense, dark matter-defined reservoirs, could begin the next stage of its journey. It could cool, condense, and fragment, eventually igniting under its own gravity to form the very first stars, ending the cosmic dark ages and flooding the universe with light for the first time. Those first brilliant beacons and the miniature galaxies that hosted them did not form at random. They sparked to life at the precise intersections of the dark matter scaffolding, their locations chosen by the silent, gravitational hand of the unseen universe. The importance of this head start cannot be overstated. Without dark matter's early initiative, the formation of stars and galaxies would have been catastrophically delayed, and the universe we see today would be unrecognizable. Normal matter, working alone, was far too inefficient. The gentle gravitational tugs between atoms were simply too weak to overcome the universe's rapid expansion and pull together significant structures in the time available. The process would have been like trying to build a sandcastle, one grain of sand at a time on a beach being constantly washed by waves. Dark matter provided the pre-built forms, the buckets and molds that allowed the sand to be gathered and shaped all at once. It provided the collective gravitational muscle that normal matter so desperately lacked. If our cosmos had been composed solely of the atoms we know and love, the first galaxies might not have formed for tens of billions of years, if at all. The universe would be a much darker, emptier, and far more lonely place, a diffuse sea of hydrogen gas with only the rarest and faintest of stellar glimmers. There would be no grand spiral galaxies, no brilliant quasars, no cosmic web, and certainly no planets or life to ponder its own existence. This foundational role establishes dark matter not as a minor player or a late addition to the cosmos, but as the very first builder, the master mason of the universe. Long before the first star ever flickered, its location was being decided by the subtle, gathering pull of an invisible substance. The magnificent celestial structures we now observe through our telescopes, from the smallest dwarf galaxies to the largest superclusters, are all the direct descendants of those initial dark matter seeds. They are the visible, luminous expression of a hidden architecture, a testament to a construction project that began in total darkness. Every galaxy we see is therefore a dual entity, a brilliant city of stars and gas, forever anchored at the heart of a much larger, invisible sphere of dark matter, a silent partner whose gravitational embrace made everything we hold luminous possible. So how does this invisible framework actually translate into the brilliant, structured galaxies we see scattered across the cosmos? The answer lies in a grand, cosmic construction project known as the hierarchical model, a bottom-up process where the universe builds from the small to the large, and at every single stage, dark matter is the foreman, the architect, and the primary building material. Picture the early universe not as a place of giant, fully formed galaxies, but as a sea of tiny, dark matter ripples. These ripples, amplified by gravity over millions of years, were the seeds of everything to come. The smallest ripples collapsed first, forming the very first dark matter halos, which might have been no more massive than a single star today. But gravity is a patient and relentless force. These small halos began to attract each other, merging and colliding, gradually assembling into larger and larger structures over billions of years. It's a cosmic game of consolidation, where tiny villages of dark matter slowly merge to form towns, then cities, and eventually the vast metropolitan clusters we see today. This entire process, this slow, gravitational assembly, is the hierarchical model, and it is a story written almost entirely by the invisible hand of dark matter. Without these initial dark matter seeds and their propensity to clump, the gas in the early universe would have had nothing to gather around, and the magnificent diversity of galaxies would never have emerged from the primordial darkness. Once a dark matter halo reaches a certain size, it becomes a powerful gravitational attractor for the normal baryonic matter, the hydrogen and helium gas that was also present in the early cosmos. This is where the invisible blueprint begins to manifest in light. Think of a dark matter halo as a deep, spherical well in the fabric of spacetime. The ordinary gas swirling in the cosmos feels this gravitational pull and begins to cascade down into the well, much like water flowing into a drain. But this gas has a critical property that dark matter lacks. It can lose energy. As the gas particles collide and interact, they can radiate away their energy in the form of light, a process known as radiative cooling. This cooling is absolutely essential. It allows the gas to shed its initial motion and settle into a rotating disk at the center of the dark matter halo. Without this ability to cool, the gas would simply remain as a hot, puffy cloud, unable to condense further. As this gas disk grows denser and denser, it eventually reaches a tipping point where local regions within the disk collapse under their own gravity, igniting the nuclear furnaces of the first stars. A galaxy is born. In this way, every single galaxy, from the smallest dwarf to the largest spiral, is fundamentally a luminous settlement that formed at the bottom of a deep, dark matter gravitational well. The intimate connection between a galaxy and its dark matter halo goes even deeper, dictating the galaxy's very personality, its size, its shape, and how it moves. Astronomers have discovered that the properties of the dark matter halo act as a kind of cosmic destiny for the galaxy growing within it. For instance, the total mass of the halo largely determines how big the resulting galaxy can become, funneling more or less gas into the central region. But perhaps the most fascinating link is between the halo and a galaxy's rotation, which in turn shapes its iconic form. Spiral galaxies, like our own Milky Way with their graceful, pinwheeling arms, are almost always found within halos that have a significant amount of overall spin, or angular momentum, inherited from the cosmic web. As the gas falls into this spinning halo, it conserves that angular momentum, naturally settling into a fast-rotating, flattened disk. The dark matter halo itself remains a vast, roughly spherical cloud, but its initial spin imprints itself onto the visible galaxy, creating the majestic spirals we are so familiar with. In contrast, giant elliptical galaxies, which are more like vast, roundish or football-shaped swarms of old stars, are thought to be the products of major galactic mergers. When two large spiral galaxies and their dark matter halos collide and merge, the incredible gravitational chaos disrupts their delicate disks, violently randomizing the orbits of stars and gas to form a much puffier, ellipsoidal structure. The properties of the visible galaxy are, therefore, a direct reflection of the history and nature of its invisible dark matter host. This process of galaxy formation, however, is not a simple, one-way street where gas flows in and forms stars until all the fuel is gone. It is a dynamic and often violent balancing act regulated by powerful feedback mechanisms. Imagine a young galaxy with gas cooling efficiently and forming stars at a ferocious rate. The most massive of these stars live fast and die young, exploding as spectacular supernovae. These explosions inject a tremendous amount of energy back into the surrounding gas, heating it up and even driving powerful winds that can blow it right out of the galaxy. At an even larger scale, supermassive black holes at the centers of galaxies can become active galactic nuclei, devouring material and firing out jets of energy that can heat gas across the entire halo, preventing it from cooling and forming new stars. This feedback is the universe's built-in thermostat. Without it, galaxies would convert their gas into stars with breathtaking speed, burning through their fuel in a short, brilliant burst and then fading to darkness. Feedback processes driven by the stars and black holes themselves act to limit their own growth. They blow bubbles in the gas, temporarily shutting down star formation and allowing the galaxy to evolve more slowly and steadily over billions of years. This creates a complex, self-regulating dance. Dark matter's gravity pulls the gas in, while stellar and black hole feedback pushes it out. The beautiful, balanced galaxy we see today is the result of this billions of years-long negotiation between the relentless pull of the dark and the explosive feedback of the light. This intricate interplay between the invisible and the visible is what gives us the stunning diversity of the galactic population we observe across the universe. From the delicate, star-forming spirals with their clear disks and blue-tinged arms, to the red and dead ellipticals filled with ancient stars, to the tiny, diffuse dwarf galaxies, each one is a unique outcome of the specific conditions within its dark matter halo and the complex astrophysical processes that played out within it. The dark matter provides the gravitational stage and the overall structure, while the baryonic physics, the gas cooling, star formation, and explosive feedback writes the detailed script. Galaxies are not simply isolated islands of stars. They are dynamic ecosystems, deeply connected to and shaped by their dark matter foundations. They are the visible blossoms on an invisible trellis, their brilliant colors, and forms a direct expression of the hidden architecture that has supported and guided their growth since the dawn of time. Just when cosmologists thought they had a solid grasp on the cosmic recipe, a persistent and nagging discrepancy has emerged, one that refuses to fade away with more precise measurements. This puzzle is known as the Hubble tension, and it centers on a single, crucial number, the Hubble constant, denoted as h0. This value represents the current expansion rate of our universe, telling us how fast galaxies are receding from us for every million parsecs of distance. It is one of the most fundamental parameters in all of cosmology, the very yardstick we use to measure the cosmos's scale and age. For decades, the goal was to pin down this number with ever greater accuracy, but instead of converging on a single, agreed-upon value, our two most reliable methods have begun to stubbornly disagree, creating a rift that threatens to reveal something new and unexpected about the universe's workings. The heart of the tension lies in a stark difference between how we measure the universe's present-day expansion and how we predict it should be expanding based on its ancient past. On one side, we have what's called the late universe or distance ladder method. This approach is like cosmic cartography, building a chain of measured distances to nearby stars and galaxies. It starts with incredibly precise parallax measurements from satellites like Gaia, which give us the distance to pulsating stars known as Cepheid variables within our own galactic neighborhood. Because we know the intrinsic brightness of these cepheids, they act as standard candles. We can then find these same types of stars in more distant galaxies that also host Type Ia supernova, another, even brighter class of standard candle. By carefully calibrating this cosmic ladder, astronomers can measure distances to far-off supernova and directly calculate the Hubble constant from their observed recession speeds. This method, championed by teams like the one led by Adam Rees, gives us a very local, direct measurement of how fast the universe is expanding right now. And the answer it consistently provides is a value around 73 kilometers per second per megaparsec. On the other side of the debate is the early universe method, which uses the cosmic microwave background as its ultimate guide. The Planck satellite, for instance, mapped the CMB's subtle temperature fluctuations with exquisite detail. Scientists then feed this fossilized snapshot of the infant universe into the supercomputer-powered Lambda-CDM model, our standard model of cosmology that includes dark energy, cold dark matter, and normal matter. The model then runs the entire history of the universe forward in time, 13.8 billion years, to predict what the Hubble constant should be today, given that specific starting point. This is not a direct measurement of the current expansion, but a prediction based on our deepest understanding of cosmic evolution. And this method yields a different, consistently lower number, around 67 kilometers per second per megaparsec. Now, a difference of about 6 kilometers per second might not sound like much, but in the world of precision cosmology, it's a chasm. The uncertainty in each measurement has been squeezed down to such a tiny margin, less than 2%, that the chance this discrepancy is a simple statistical fluke is becoming vanishingly small. It's like two groups of the world's best watchmakers building a clock based on the same blueprint, and one group consistently produces a clock that ticks measurably faster than the other. The blueprint itself, our Lambda-CDM model, might be the source of the problem. This tension has not gone away with more data. In fact, it has only solidified, growing from a curious anomaly into cosmology's most pressing unsolved problem. So, what could be causing this rift in our cosmic measurements? Scientists are exploring a fascinating menu of possibilities, each more exotic than the last. One compelling idea is that our inventory of the early universe might be incomplete. The standard model includes dark matter, dark energy, and normal matter, but perhaps there was an additional, fleeting component in the primordial cosmos. Theorists have proposed the existence of dark radiation, which could be an unknown, lightweight particle that streamed freely through the early universe, influencing how quickly those first sound waves traveled through the plasma. The presence of such a particle would subtly alter the pattern of the cosmic microwave background, which would, in turn, change the predicted value for the Hubble constant when the model is run forward. Adding just a pinch of this exotic ingredient could be enough to bridge the gap between the early and late universe measurements. Another tantalizing possibility is that dark energy itself is not the simple, constant force we have assumed it to be. What if its strength has changed over time? If dark energy was a little bit stronger in the universe's adolescent years than our models account for, it would have given the expansion an extra nudge, making the universe expand just that little bit faster than predicted, potentially bringing the early universe prediction into alignment with what we see locally. This would point toward a more dynamic form of dark energy, like the quintessence field we discussed earlier, rather than Einstein's static cosmological constant. Alternatively, the issue might lie with dark matter. Perhaps dark matter possesses properties we haven't yet accounted for, such as a slight ability to interact with itself or with radiation, which could have modified the growth of cosmic structure in a way that affects the expansion history. There is also a more conservative, though increasingly unlikely, explanation that there is an unaccounted for systematic error in one of the measurement techniques. Perhaps our cosmic distance ladder has a hidden rung that is slightly warped. Maybe there is an unknown subtlety in the physics of Cepheid variable stars or type Ia supernova that is biasing the local measurement. Teams of astronomers are working frantically to rule out every possible mundane error, using new methods like gravitational waves from merging neutron stars, which provide a completely independent way to measure cosmic distances. So far, however, these independent checks have tended to side with one camp or the other, deepening the mystery rather than resolving it. The Hubble tension is far more than a technical disagreement over a number. It is a potential gateway to a deeper level of physical understanding. In the history of science, it is often the tiny, persistent anomalies, the slight wobble in Mercury's orbit, the unexplained shift in starlight during an eclipse, that have heralded the greatest breakthroughs, forcing us to abandon comfortable theories and embrace new, more complete visions of reality. The Hubble tension has all the hallmarks of such a moment. It is a clear, data-driven signal that our otherwise spectacularly successful standard model of cosmology might be missing a crucial piece of the puzzle. Resolving this tension is now a primary driving force in cosmology, guiding the design of new telescopes and the direction of theoretical research. It represents the thrilling possibility that we are on the verge of discovering not just what the universe is made of, but something new about how its fundamental components behave, pushing us once again to rewrite the textbooks on the cosmos. But this accelerating expansion does far more than just dictate the future arrangement of galaxies. It fundamentally rewrites our understanding of time and connectivity on the grandest of scales. We often think of time as a universal river, flowing at the same rate for everyone, everywhere, connecting all events in a single, unbreakable chain of cause and effect. Yet, in a cosmos dominated by dark energy, this intuitive picture begins to fray at the edges, revealing a reality where time itself becomes a local and increasingly isolated phenomenon. The key to this startling shift lies in the concept of a cosmic event horizon, a boundary that is, in a strange way, the opposite of the one surrounding a black hole. A black hole's event horizon is a point of no return for anything falling in. The cosmic event horizon, however, is a point of no return for anything trying to reach us. As the space between galaxy clusters expands at an accelerating rate, there comes a point for every distant galaxy where the space between us is stretching faster than light can travel across it. When a galaxy crosses that threshold, the light it emits from that moment onward, no matter how brilliant the star or cataclysmic the event, is fundamentally doomed. It will be trying to swim against a current of expanding space that is simply too swift, like a swimmer in a river that is widening faster than they can paddle. That light will never, ever reach us. The galaxy, from our perspective, doesn't just get fainter. It winks out of existence, frozen in time at the moment it crossed the horizon, its final photons stretching into undetectable, infinite wavelengths as it is carried away into the impenetrable dark. This process carves out a finite and ever-shrinking sphere of reality that we can ever hope to interact with or know about. Imagine our observable universe not as a static stage that is gradually being illuminated by light from farther away, but as a glowing island in an ever-widening black ocean. Today, this island is vast, containing hundreds of billions of galaxies. But as dark energy continues its work, the shoreline of our island is actively eroding. One by one, the galaxies at the edge will vanish beyond this cosmic shoreline, their light unable to bridge the growing void. In the far future, trillions of years from now, an astronomer in our Milky Way or whatever galaxy it has merged with will peer into a sky that is almost perfectly black. The entire cosmic context for our existence, the evidence of the Big Bang, the receding galaxies, the brilliant tapestry of the cosmic web, will have been erased from their view. Their universe will consist of their own local cluster of gravitationally bound galaxies, adrift in an incomprehensible emptiness, with no clues whatsoever to suggest a larger, more vibrant cosmos ever existed. This is the ultimate isolation, a future where the universe's history is lost, not to fire or ice, but to the simple, relentless geometry of accelerating space. This has a profound and chilling consequence for the very nature of causality, the principle that cause must precede effect. Causality is enforced by the speed of light, for one event to influence another. A signal, whether it's a ray of light, a gravitational wave, or a radio transmission, must have time to travel between them. But as our cosmic island shrinks, so too does our sphere of causal influence. Events occurring beyond our horizon cannot affect us, and we cannot affect them. The universe fractures into a collection of disconnected causal patches, isolated islands of reality that are forever unaware of each other's existence, their fates completely decoupled. This imposes a fundamental and absolute limit on knowledge and exploration. No future technology, no matter how advanced, could ever allow us to visit or even receive a signal from a galaxy that has passed beyond our horizon. The ambition to one day explore the entire cosmos, a dream of science fiction, is ultimately doomed by the physics of dark energy. The universe is not just becoming emptier, it is becoming a collection of separate, non-communicating universes, each living out its own timeline in solitary confinement. In this context, the arrow of time, the perceived flow from past to future, takes on a new and somber character. In our local human experience, the arrow of time is tied to increasing complexity and the rise and fall of structures, from the birth of stars to the processes of life. But on the ultimate cosmic scale, the arrow of time, driven by dark energy, points toward disintegration, isolation, and the heat death of this shrinking causal patch. The future is not one of greater connection or understanding, but of deepening silence and disconnection. Time itself, in this grand narrative, is not a neutral backdrop but an active force shaped by the dark components of the universe. The dark matter that gathered the galaxies and the dark energy that is now tearing them apart are not just actors on the stage of time. They are the directors, shaping the very flow and connectivity of the cosmic story. The dark side of the universe, therefore, doesn't just fill the space between the stars. It dictates the ultimate limits of our experience, carving out a finite domain within the infinite and steering the long-term destiny of time toward a quiet, lonely, and unknowable end. This grand quest to understand the dark universe inevitably leads us to a monumental challenge, one that stands as the single greatest ambition in all of physics: to weave the disparate threads of reality into a single, seamless tapestry. For centuries, we have been studying the cosmos with a kind of split vision. On one hand, we have the standard model of particle physics, a triumph of human intellect that catalogues the known particles and forces with breathtaking precision. It explains the atoms in our bodies, the light from the sun, and the nuclear reactions that power the stars. It is, without exaggeration, one of the most successful theories ever devised. Yet, for all its glory, it is utterly silent on the 95% of the universe that is dark matter and dark energy. It's as if we have a perfect, detailed map of a single, glittering city, but we are completely unaware of the vast, dark continent upon which that city is built. The ultimate goal, the holy grail of modern physics, is to find a single, coherent theory that seamlessly unites these two worlds, the brilliant, well-lit city of the Standard Model with the mysterious, uncharted dark sector. One of the most elegant and long-pursued bridges to this hidden continent is a concept known as supersymmetry. Imagine that for every known particle in the Standard Model, every electron, every quark, every photon, there exists a hidden superpartner. For the electron, there would be a selectron, for the quark, a squark, for the photon, a photino. These superpartners would be heavier and more elusive than their familiar twins, which is why we haven't yet observed them in our particle colliders. Supersymmetry is attractive for many reasons, but one of its most compelling features is that it provides a perfect, ready-made dark matter candidate. In most versions of the theory, the lightest of these superpartners, often the neutralino, would be stable, electrically neutral, and only interact weakly with normal matter. It would, in essence, be a WIMP, a weakly interacting massive particle, the very candidate that has been the focus of so many direct detection experiments for decades. Supersymmetry would not be an add-on to the Standard Model. It would be a natural extension, a deeper layer of symmetry in nature that effortlessly explains the existence of the dark matter that holds our galaxies together. While the Large Hadron Collider has so far not found the clear signatures of these superpartners, pushing them to higher and higher energies, the mathematical beauty of supersymmetry keeps it a vibrant, though increasingly pressured, avenue of exploration. If supersymmetry represents a new layer of particles, then the idea of extra dimensions proposes a new layer of space itself. We are intimately familiar with the three dimensions of space: length, width, and height, and the one dimension of time. But what if the universe actually has more, tiny, curled-up spatial dimensions that are so small we simply cannot perceive them? In some of these theories, the fundamental strings of string theory vibrate in these higher dimensional realms. This concept offers a radical rethinking of gravity. In our familiar three-dimensional world, gravity is incredibly weak compared to the other forces. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth. The reason these theories suggest is that gravity is not confined to our three-dimensional brain of existence. It is diluted because it can leak out into these extra dimensions. This also opens up a stunning possibility for dark matter. What if dark matter isn't a particle living in our three-dimensional space at all? What if it is actually a vibration or a particle that is confined to a different dimensional brain, parallel to our own? It would be all around us, yet completely invisible and intangible, interacting with our world only through the faint, leaky channel of gravity. It would be like living on one side of a two-dimensional sheet of paper, completely unaware of a civilization living on a parallel sheet just a microscopic distance away, yet feeling the faint, mysterious tug of their gravity. This is not just science fiction. It is a serious, if highly speculative, framework that attempts to explain the profound weakness of gravity and the ghostly nature of dark matter in one grand conceptual sweep. The most ambitious of all these unifying frameworks is string theory. At its heart, string theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. Just as a single violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in different ways to produce the entire menagerie of particles we see in the Standard Model. One vibration gives you an electron, another a quark, another the photon. The allure of string theory is its breathtaking scope. It is, by its very design, a theory of quantum gravity, an attempt to seamlessly merge the world of the very small, governed by quantum mechanics, with the large-scale structure of spacetime described by general relativity. Within its mathematical structure, the dark sector finds a potentially natural home. The theory doesn't just predict one type of particle that could be dark matter. It predicts a vast landscape of possibilities, from specific vibrational modes of the strings themselves to other extended objects known as brains. The action, that lightweight dark matter candidate, emerges elegantly from string theory. Even dark energy can be accommodated within its framework, though it often leads to the controversial multiverse landscape, where the value of the cosmological constant is an environmental accident. String theory is not without its profound challenges. It requires extra dimensions. It has yet to make testable experimental predictions, and its mathematical complexity is staggering. But it represents the most comprehensive attempt to date to write a single, unified equation that describes everything from the dance of quarks to the fate of the cosmos. The pursuit of this grand unification is more than an academic exercise. It is a fundamental human drive to find coherence and order in the universe. We are haunted by the dissonance of having two incredibly successful but disconnected descriptions of reality. The Standard Model explains the 5% we see with peerless accuracy, while the Lambda-CDM model of cosmology explains the behavior of the 95% we cannot see through their gravitational effects. But a complete theory of physics cannot have two separate rulebooks. Unifying them is the necessary step to answering the deepest why questions. Why is the universe made of the specific particles it is? Why do the forces have the strengths they do? Why is there dark energy, and why does it have the infinitesimally small value that allows our existence? The quest to connect the dark sector to the Standard Model is the journey to find a single origin story for all of reality, a theory that would not just fill in the blanks on our cosmic map, but reveal why the map had to be drawn that way in the first place. It is a pursuit that operates at the very frontier of human thought, where mathematics, imagination, and the stubborn voice of observational data converge in an effort to read the hidden signature of the cosmos, a signature written in both light and darkness. Now let's step back from the cosmic frontier for a moment and bring these colossal ideas down to Earth, because when we talk about the dark universe, it's a phrase that can easily be misunderstood. The words dark matter and dark energy sound like something straight out of a fantasy novel or a superhero movie, and that can lead to some pretty common mix-ups. It's vital to clear the air and demystify what these terms truly mean. First and foremost, dark in this context is not a moral judgment. It doesn't mean evil, sinister, or dangerous. It is a simple, technical term used in astronomy and physics that means one thing and one thing only. It does not interact with light. Dark matter doesn't emit it, absorb it, or reflect it. It is electromagnetically blind and invisible. This is a crucial distinction to make because it separates the science from the science fiction. This leads to one of the most frequent points of confusion. People often conflate dark matter with other exotic-sounding concepts like black holes or antimatter, but these are all very different things. A black hole is an incredibly dense object whose gravity is so intense that not even light can escape it. It is a phenomenon, a region of space-time. Antimatter, on the other hand, is a form of matter where particles have the opposite charge of their normal counterparts. When matter and antimatter meet, they annihilate in a flash of energy. Dark matter is none of these. It is not a cosmic vacuum cleaner, and it is not an explosive substance. It is a pervasive, transparent substance that fills the cosmos, and its primary, and seemingly only, job is to exert a gravitational pull. To make this tangible, consider a simple but powerful analogy. Think about the wind. You cannot see the wind itself. You can't reach out and grab a handful of air and declare this is the wind. But you can absolutely see its effects. You watch the leaves rustling in a tree, you see the branches swaying, you feel it pushing against your face on a blustery day. The wind is invisible, but its influence on the visible world around you is undeniable. Dark matter is the cosmic wind. We cannot see it, but we see its effects with crystal clarity. We see it in the way stars whip around galaxies too fast, in the way light bends around invisible mass, and in the grand architecture of the cosmic web. The galaxies are the leaves rustling in the tree, telling us without a doubt that an unseen force is at work. Perhaps the most mind-bending realization is that this isn't some distant, abstract phenomenon. You are not just an observer of the dark universe, you are immersed in it right here, right now. Our entire solar system, our planet, and every one of us is currently swimming through the Milky Way galaxy's vast halo of dark matter. Trillions of these elusive particles are streaming through your body every single second like a silent, cosmic, ghostly rain, and you feel absolutely nothing. There is no tingle, no sense of cold, no physical sensation whatsoever. This is because, as far as we can tell, dark matter doesn't interact with the atoms that make up your body in any way other than the faintest whisper of gravity, which is far too weak to notice. It passes through the floor beneath your feet, through the walls of your home, and through you as if you weren't even there. This complete lack of interaction is precisely what makes it so difficult to detect, but it also means it is perfectly harmless to us on an individual level. The dark universe is not a threat. It is the fundamental, if invisible, backdrop of our existence. Addressing these kinds of misconceptions is not just an academic exercise. It is a cornerstone of building a scientifically literate society. When the public understands what dark matter and dark energy truly are, and what they are not, it fosters a deeper, more genuine appreciation for the discoveries being made. It transforms these concepts from sensationalized, sci-fi buzzwords into the profound scientific mysteries they truly are. This understanding is the bedrock of public support for the kind of fundamental, curiosity-driven research that drives these fields forward. The incredible experiments we've discussed, from the deep underground detectors to the space telescopes mapping the void, are funded by societies that value the pursuit of knowledge for its own sake. Clear, accurate, and engaging communication is the essential bridge that connects the complex work happening at the frontiers of theoretical physics and cosmology with the everyday person who is inherently curious about the universe they live in. By demystifying the darkness, we don't just share knowledge, we invite everyone to share in the wonder and the humbling reality that we are only just beginning to perceive the true nature of our reality. What if the greatest technological benefits of exploring the cosmos come not from studying the light, but from our relentless pursuit of the darkness? The quest to detect dark matter and measure dark energy is one of the most technologically demanding endeavors humanity has ever undertaken. It forces us to operate at the very edge of the possible, and in doing so, it consistently spins off innovations that ripple out, transforming medicine, computing, and our daily lives in ways we never anticipated. This is a powerful story where the search for fundamental knowledge for its own sake becomes a powerful engine for practical progress, proving that investing in pure curiosity often yields the most valuable returns. Consider the extraordinary challenge of building a dark matter detector. To have any hope of hearing the faint whisper of a WIMP collision, scientists must create an environment of near-perfect silence, shielded from the constant background noise of the natural world. This demand for absolute radio purity has catalyzed a quiet revolution in materials science. The techniques developed to purify thousands of kilograms of liquid xenon for experiments like LUX Zeppelin and Xeno NNT are nothing short of alchemical. Engineers have learned to filter this noble gas to a level where there is less than 1 atom of a radioactive contaminant for every trillion atoms of xenon. This isn't just a laboratory trick. This ultra-purification technology has direct applications in the semiconductor industry, where the tiniest impurity can ruin a silicon wafer, and in medical imaging, where ultra-pure crystals are essential for creating more sensitive and accurate PT and MRI scanners. The quest to see the invisible has given us new eyes for diagnosing disease. Then there is the cold. To make their detectors exquisitely sensitive, physicists must cool them to temperatures within a fraction of a degree of absolute zero, the point where all atomic motion nearly ceases. Developing the cryogenic systems to achieve and maintain these profound temperatures for large, complex apparatuses has pushed the entire field of low-temperature physics forward. The sophisticated pulse tube refrigerators and dilution refrigerators that keep these experiments colder than the void of outer space are now finding uses in preserving biological samples, cooling the superconducting magnets in next-generation MRI machines to make them more efficient and affordable, and are even being adapted for the nascent quantum computing industry, where qubits must be kept at near zero temperatures to maintain their fragile quantum states. The technology we built to listen for dark matter is now helping to build the computers of tomorrow. Perhaps the most widespread impact, however, comes from the sheer deluge of data these cosmological projects generate. The Vera C. Rubin Observatory's legacy survey of space and time won't just take pictures of the sky. It will produce a data stream equivalent to taking a full high-definition movie of the entire visible universe, night after night for 10 years. Processing, storing, and analyzing this avalanche of information is a problem of such magnitude that it has forced computer scientists to invent entirely new ways of handling big data. The machine learning algorithms initially developed to pick out the subtle, sheared shapes of galaxies for weak gravitational lensing maps, to distinguish the signature of dark matter from billions of starry images, are now being adapted for completely different tasks. They help radiologists spot early-stage tumors in medical scans with greater speed and accuracy. They enable facial recognition software, and they help financial institutions detect fraudulent transactions. The computer code written to map the cosmic web is now helping to navigate the complex web of human health and commerce. Even the most abstract theoretical pursuit, the effort to understand the vacuum energy of empty space, holds a distant but tantalizing promise. While it remains a profound puzzle, the very act of probing the fundamental nature of spacetime and energy pushes the boundaries of quantum field theory. History has shown us that today's esoteric physics is tomorrow's transformative technology. The quantum mechanics that once baffled Einstein led directly to the transistor and the laser, the bedrock of our modern digital world. While it is speculative, gaining a deeper mastery over the energy of the vacuum itself could, centuries from now, open up possibilities for energy generation or propulsion that are the stuff of science fiction today. The journey to understand dark energy is a long-term investment in the fundamental principles that may one day empower our civilization in ways we can barely imagine. This pattern is not a coincidence. It is a recurring feature of how science progresses. When you set a goal that seems almost impossible, like finding a particle that passes through solid rock or measuring the energy of nothingness, you cannot simply incrementally improve existing tools. You are forced to invent entirely new ones. You push materials to new levels of purity. You create colder temperatures, and you teach computers to see patterns they have never seen before. These technological breakthroughs, born from a specific curiosity-driven need, inevitably find their way into the broader economy, improving our health, powering our communication, and expanding our capabilities. The search for the dark universe, therefore, is far more than an intellectual exercise. It is a powerful catalyst, a crucible of innovation that forges the advanced technologies of tomorrow while answering the most profound questions about our cosmic home. The light we shed on the darkness, it turns out, illuminates our own world in return. And so we reach the end of our journey, a voyage that began by staring up at the familiar stars and has led us into the heart of a profound and humbling cosmic mystery. We have traced the path from the first puzzling observations of whirling galaxies to the shocking revelation of an accelerating cosmos, uncovering a universe where the light we see is a mere 5% of the whole story. The other 95%, the silent, dominant majority of all existence, is composed of dark matter, the universe's invisible skeleton, and dark energy, the mysterious force tearing the cosmos apart. We have seen how scientists use the bending of light and the faint afterglow of creation to map the unseen, and how they build exquisitely sensitive machines deep underground to listen for a whisper from the dark. This exploration has forced us to confront a reality where the true nature of the cosmos is fundamentally hidden from our senses, a philosophical shift that redefines our place in the grand scheme of things. Yet, this is not a story of final answers, but one of magnificent questions. The fundamental identity of dark matter particles and the true origin of dark energy's repulsive force remain two of the most stubborn and exhilarating puzzles in all of science. But the search itself is a testament to the human spirit, our relentless curiosity, the drive to understand the world around us no matter how well it hides its secrets, is pushing technology to its absolute limits. The quest to detect the undetectable is leading to breakthroughs in materials science, computing, and sensor technology that ripple out into our daily lives, from advanced medical imaging to the way we handle vast streams of data. The pursuit of pure knowledge, it turns out, is one of the most powerful engines of practical innovation we have. So the next time you find yourself under a clear night sky, let this new perspective sink in. Those glittering points of light, those swirling galaxies captured in telescope images, are not the main event. They are the decorative glitter on the surface of a vast, deep, and profoundly dark ocean. We are only just beginning to dip our toes into its waters, to feel the currents of dark matter and sense the tide of dark energy. The exploration is far from over. New telescopes, new detectors, and new brilliant minds are joining the hunt every day, each one bringing us closer to the next great revelation. Who knows? The person who finally sheds light on this cosmic darkness, who cracks the code of the invisible universe, might be looking up at those very stars right now, filled with the same wonder that has driven this quest for generations. The greatest discoveries in science are still ahead of us, waiting in the dark. Let us know what you think about this cosmic mystery in the comments. And if you enjoyed this journey to the edge of our understanding, be sure to subscribe for more explorations of the universe's